right through to 2:30 before our next 15-minute break. Thanks very much. So it appears that the files were messed up on that log score example that I was trying to do before lunch, and I haven't had time to fix that. So I'm going to keep trying to fix it during the remaining 15-minute breaks. At the moment, the web page has some broken links on it because I've been moving things around a bit, and I'm going to write some files over again. So, we'll get back to that later. In the meantime, we were talking about the fact that it's hard to do this calibration cross-validation story stably with data sets like the NB10 data that have a relatively small number of outliers that are characterizing the T-ness of the data, because you don't have enough outliers for at least one or more of them to fall into each of the data sets with high probability. So that makes it hard to do validation. We were on page 416 of this book chapter, in which I was essentially saying the same sort of thing. We were looking at the parameter estimates across the different subsets and seeing that they were vastly different sometimes, arising from the problem that sometimes there isn't an outlier in one of the subsets. So another way to put the difficulty, like it says here, looking at the full NB10 data set in the previous table, is that there are, quote, only 3 outliers in the entire data set, and the presence or absence of any one of those has a high degree of influence on the estimates. So elsewhere, I have performed the obvious analysis to remedy this problem. I've repeated the CCV algorithm across many random MVC partitions and averaged the results. And in this chapter, I didn't reproduce those results here, and I won't today either. But the conclusion from this broader analysis is that the T model is a good basis for stopping the iterative step in calibration cross-validation and proceeding to the final step. So remembering back to the algorithm itself, we started by partitioning. We then did an iterative process going back and forth between the modeling and validation data sets in B and C through step D until we do get good validation. And now the idea is to fit the T model to the entire data set in modeling plus the data in validation, and now see how good the results are in the calibration data set. So let's do that. So as it says at the bottom of page 416, the third row in that table on the next page gives posterior summaries from fitting the T model to the 75 observations that you get by taking the M and V subsets and merging them together. And the left panel in the figure that's about to follow gives the calibration plot for this fit when applied to the calibration data set. So first of all, the third row in this table on page 417 shows that it is producing answers that are quite similar to those that we got from the modeling subset alone, where things did actually validate pretty well. And also you'll see, just for grins, I went ahead and fit the T model to the entire data set just to see how different things were there. And again, you can see that the answers from the M union V part of things are actually quite close to the answers from the whole data set. So let's look at this next calibration plot. That should be down here. So left-hand panel in figure 20.4, we have the calibration plot for the T model fit to the data in modeling union validation, and then validated in the calibration data set. And you can see the calibration is middling okay, not perfect, and it's because the intervals aren't quite wide enough to do their job perfectly. And then when I tried to validate in the entire data set using M, V, and C all together, which is what you would have done if you used the analysis where you pretended that you knew the T model was right all along, you find interestingly that it also is coming up a little short in the department of producing intervals that are wide enough. So perhaps the T model has indeed slightly overfit the data. And so on the basis of, I think that calibration cross-validation is done now for this small data set. And here would be my conclusions. It turned out that the T-model had 95% intervals, including the actual data values, about 88% of the time in the calibration data set. So I would report the results from only the modeling union validation part of things, namely the block of metal called NB10 weighed about 404.0 micrograms below the nominal weight of 10 grams, give or take about 0.50. So I'm using the results from M union V together. And a 95% interval for its weight runs from 403.0 to about 404.9. And then secondly, the second conclusion I would draw is that the iterative modeling process that led to the inferential conclusion in A is actually slightly somewhat overconfident in its ability to predict future data values not used in the model fitting, with nominal 95% predictive intervals for future observations, including the truth about 88% of the time, give or take about the usual Bernoulli binomial standard error, namely 0.88 times 0.12 over 25 square rooted times 100 to make it into a percent, and that's about 6.5% percentage points. So essentially, we think that the level of calibration of this iterative fitting process on new data is somewhere around 88%, give or take about 6 or 7%. And so that means that if we'd had more data in the calibration data set to really see what's going on, we wouldn't be surprised to see a level of calibration external to the fitting process anywhere from about 88 plus or minus 2 of those standard errors, going all the way up to 100% and going all the way down to about 75%. So this shows another story about why it's difficult to do this in small samples. If you only have 100 observations and you try to leave 25 of them out for external calibration, 25 is not a lot of data points to do external calibration on, and so you have quite a bit of uncertainty about how well calibrated the process is. The third part of this chapter is not, I'm not going to brief it in this class. It talks about a different way to think about Bayesian nonparametrics. Actually, no, the third part, 20.3, we looked at already about Bayesian nonparametrics for the sampling distribution. And the final part, I'm not going to brief. It talks about how to be nonparametric, fully nonparametric, about putting down a prior as well. It concerns the T-machine problem that I believe I've told you guys about. I think, did I tell you about that in here? About my going to UCLA and trying to get data, or rather get tea from a machine that claimed it might give me a free cup of tea every now and then. Some people are nodding their heads, yeah. So there's more about that example if you ever want to read it. So that pretty well exhausts what I wanted to share with you about this chapter. It's a specific example of how to do calibration cross-validation, and I'll also be doing it next week as part of our wrap-up on a bigger and more interesting data set, CCV and bigger data set. So let's return now to the main line on part 5. And try to address those issues that we've been ducking for so long. How do you know when one model is better than another? And how do you know when a model is good enough to stop looking for even better models? And as I may have mentioned last time, but it certainly bears repeating, Q1 and Q2 here at the bottom of page 44 sound like they're utterly fundamental questions. How could there be any question lurking underneath a question like, is Model 1 better than Model 2? But actually, it seems to me that it's not quite bedrock yet. There is a question even deeper, even below that question, because question 1 itself does not define the meaning of the word better. And so if I asked you, is Model 1 better than Model 2, you have a right to ask me another question in return, namely, better for what purpose? And similarly, if I ask you the question, is Model 1 good enough to stop looking for better models, you have a right to ask me that same basic question, good enough for what purpose? And I think I have mentioned this briefly last time in the following sense. Think about a purpose for which a very crude description of what's going on is sufficient to make a decision, for example. Something like the Challenger space shuttle disaster, where it was so blatantly obvious looking at the data relating temperature to O-ring failure that only a relatively crude analysis of the data was needed to see that the right thing to do was not to launch at 32 degrees. For that purpose, a crude model is enough, is sufficient. And so you can stop with a crude model. And even though there might be some other model that's better than that model for some more refined purpose, it's not better for the purpose of answering a crude question. So basically, even though the question, is Model 1 better than Model 2, sounds very fundamental, it's not yet fundamental. Better for what purpose? Question 2 sounds completely fundamental. Is Model 1 good enough to stop looking for a better model? Not fundamental yet. Good enough for what purpose? And of course, as soon as you bring purpose into the story with respect to model choice, you then have to start talking about values. How is it that one thing is better than another for the purpose that you have in mind? And that means that you're back in the world of utility and decision making. So as it says at the top of page 45, this leads me directly to the second of my 4 principles that I'm sharing with you in this part 5 of the lecture notes. The first one was the calibration principle. It's a good idea to keep track of how often your methods for learning about the world get the right answer. That's what the calibration principle says. And now the modeling as decision principle says, making clear the purpose to which the modeling will be put transforms model specification into a decision problem, which should be solved by maximizing expected utility with the utility function tailored to the specific problem under study. Do people do this every day of every week of every year? The answer is no. This is hard to do. I'll take a few minutes now to show you the one time in my entire career I have pursued it and been able to do it successfully. And it's that example I was telling you about before, where we're interested in building a scale that measures how sick patients are when they arrive at the hospital with pneumonia. And we have to choose amongst predictor variables that vary tremendously in how much they cost to collect. So let's take a break and from this line of reasoning here and go look at that story, which is now on the course webpage. So there are 2 places to look at it. One is in the JASA paper that you can read at your own convenience. It is not very technically difficult, this paper. Certainly not anywhere near as technically difficult as this paper I was mentioning to you before about comparing, I guess it's this paper here where we're trying to come up with a new prior for variable selection. That paper is highly technical, but this one here is not that technical, and it has the bonus that if you're interested in optimization, the paper is both about Bayesian decision theory on the one hand and optimization on the other hand, because my student Fuskakis was equally interested in those 2 problems, and so he ended up writing a PhD dissertation with me at the University of Bath, in which his dissertation had strong components of both. And we're talking about comparing various methods of stochastic optimization in high dimensions. And so you've probably heard about simulated annealing. You've probably heard about genetic algorithms. There's a method that people use in the operations research literature called taboo search. And what Dimitris and I did was to compare those methods and try to create refinements to them that worked even better than the off-the-shelf versions of them, as to which of them was best at finding good models in a very big model space, because our data set there didn't just have 2 to the 56 predictors, sets of predictor subsets. It had 2 to the 83, and 2 to the 83 is about 10 to the 25. And we saw earlier today that it would have taken you almost 2 years to look at all the models with 8,000 processors going simultaneously. Here we're now, and that was 10 to the 16th, we're now in the world of 10 to the 25th. So that's another billion times longer, right? So you're not going to get a chance to look at them all. So how do you build an algorithm that moves around stochastically in model space and tries to visit the good models? So I'll leave reading that paper to you, with one exception, I think. And instead, I'm going to focus on these lecture notes, which describe the paper in a little bit more, um, discursive sort of way. Let's put it that way. Here, I'm going to download that and go here where I couldn't do a full screen on it. So here's our case study. I'm thinking of the general problem of measuring the quality of healthcare that's offered to people in hospitals. And I talked earlier in the quarter about how that is going to involve measuring a number of things that all bear upon the subject. You want to look at outcomes like mortality, and you have to look at how sick the patients are when they arrive at the hospital, because it's not fair just to compare two hospitals on their raw mortality rates if one of them is treating much sicker patients. You have places like the Cleveland Clinic and the Mayo Clinic that are meant to be funnels from all over the country for the most difficult cases, the sickest people of all. The raw mortality rate at the Cleveland Clinic and the Mayo Clinic is nothing to write home about. But that's because their patients are vastly sicker than the ones that you come to a usual hospital. So you have to measure sickness at admission and do some kind of adjustment process, which will involve comparing the observed mortality outcomes with what would have been expected at this hospital if ... and you have to fill in that if. The philosophers would call it a counterfactual sort of question. Namely, for example, you could say, compare the observed mortality rate with what you would have expected if you had taken the patients from this hospital and imagined them being treated at every other hospital in the country and aggregated those results. That would be holding the patient cohort from this hospital constant and asking, how well is the rest of the country doing with those patients? That's one of several possible counterfactuals that you could be interested in here. And I have written about that issue elsewhere. So we got to measure sickness at admission. And when you go to patients' charts and look around, this was in an era before electronic medical records, so the data in those days had to actually be obtained by going into hospitals and getting lists of all of their patient records and choosing random subsamples of those lists, and then having skilled professionals go to the room in the basement where the actual paper files sat and draw those files out, sit with them on a table, and transcribe manually information from there. In fact, what we did back in the 1980s for the RAND study that this was based on is that the nurse practitioners who were the data gatherers didn't even bring computers with them in those days because it was too expensive to give them computers. They actually just transcribed information from the patient's medical record in the hospital onto these special forms that we had given them to do so. And we took those forms back to RAND and then typed the data in and computerized it there. So quite a laborious thing to do. There will typically be in any given medical record about 100 different variables that measure one aspect or another of how sick the patient is. And those indicators vary tremendously according to what it is that you're sick with. The right thing to look at for sickness for heart attack patients turns out to be quite different than the right things to look at for pneumonia patients, obviously. There is some overlap, of course, between them both. But when you get down to the details, there's a lot of variables that are specific to the particular disease. What we did back in when we actually worked on the study for RAND is we built models, logistic regression models, in which we started with all 100 of the available variables. Actually, in pneumonia, it was 83. And then we used a good piece of technology for the time, which was what frequentists used to call backward selection from the full model. So you start with a model that has all the predictors in it, and you begin stripping away the variables one by one, where you toss away, wherever you are now, you toss away the variable that has the smallest absolute t-statistic, the one that seems to have the least predictive improvement. And then you look at that new model, and then you find the variable in that new model that has the smallest absolute t-statistic, and you keep stripping away. and looking at the adjusted R-squared until you find that you're actually starting to eat into the signal now. You're throwing away variables that do have really valuable signal in them. And then you move forward again a little bit until you reach that border where the next variable out would noticeably decrease your adjusted R-squared, and you stop. That was the state of the art in 1985 when we were doing this work. Well, can we do better? Answer, yes. A lot of things have gotten better since 1985 today. And even there was something we could have done better in the RAND study that we didn't have time to do, namely the thing I mentioned before lunch. A variable is worth inclusion in the set of predictors. The way to decide whether it's worth coming in or not is actually a bivariate criterion. Does it predict the outcome well? In this case here, we had the outcome variable of mortality. Our reasoning was, of course, people who are sicker are more likely to die. And so you take the outcome variable mortality and you make a logistic regression with that binary outcome against a whole bunch of sickness predictors. So a variable is good if it helps to predict death. And it's also good if it's cheap. Because you remember those nurse practitioners are sitting there with the chart in the basement of some hospital in rural California, let's say. And if a variable only takes 5 seconds to get from the medical record and it has strong predictive ability, it's much better than a variable that takes a minute and a half to get from the record. And that is, in fact, how we measured the costs. It was measured in typical time required to get this, and then we translated it into money based upon the rate at which these people were being paid. So there's actually a bivariate optimization here. Yes? Yes, it's true. The data may have been written down incorrectly in the actual file that was sitting in the basement of the hospital. The nurse practitioner may have transcribed it incorrectly onto our special form, and then it might have been transcribed incorrectly yet again and going from our special form to the digitized version of the data set. You're absolutely right about that. We had overreading on various stages of things. We didn't do any overreading over the shoulders of the nurse practitioners, but we did do I think, in fact, we did double data entry in going from the forms to the digitized data set. And whenever any errors were found, people went back and looked at the form and got it right. And so that's an expensive way to solve problems like that. But we did that, actually, to make sure the data were of relatively high quality. And even when you're done, you still have some fields that are medically impossible. Someone's systolic blood pressure gets written down as 600. Whereas you can't have a systolic blood pressure above about 210 or you're practically dead. And so that gives rise to a missing data problem because that value is unknown to us now. And we went through an elaborate phase lasting months in this study where we thought about various methods for trying to impute, as the verb, impute values for the missing values. Because we were quite sure that just throwing away the records that had one or more missing value was a bad approach because you'd end up losing too many records that way. Doctors often, medical researchers often impute normal values whenever a value is missing. But that's a bad idea, right? It's an easy thing to do because you know what a normal systolic blood pressure is. But what you really ought to be doing is looking at other things about the patient that would be predictive of that blood pressure and build a little prediction model. And we actually did that. We built a little separate prediction model for each predictor variable from the other predictors. And we used those predictor models on the predictors to impute what the missing predictor values would have been. So we created a data set in which all the holes, the missing holes, were filled. But even that falls short of a full Bayes analysis because what you really have every time there's a missing observation is there should be a little posterior predictive distribution. And so what multiple imputation does and what a full Bayes analysis does is it creates many copies of the data set each time all the holes having been filled from draws from those predictive distributions. And then you do a whole bunch of analyses of those complete data sets in parallel and bring the answers together. That's essentially what the right way is to deal with full uncertainty about missingness. We probably, yes, you're right. We could have done that and we didn't. You're right. That would have been a further refinement on what we did. Our costs were driven only by the time necessary to get the variable from the the chart in the basement of the hospital to our abstraction forms, but you're right, that should have been part of it as well. Okay, so we actually worked out 3 different ways to solve this problem, corresponding to those 3 papers that I put on the web page. I want to tell you mainly about the decision theoretic approach because I wanted to give you a case study of maximizing expected utility of a real decision problem, solving a science problem. And also this is an example of treating the question, is one model better than another, treating it decision theoretically as it should be. So method 1 was decision theory based. We built a utility function and maximized expected utility. Method 2 was that cost-adjusted BIC approach based on posterior model probabilities or odds. And then the third one was, as I mentioned, the cost restriction benefit analysis. We maximized predictive accuracy subject to a bound on cost. So here's something about a little flavor of what the data is like. We have P equals 83 sickness indicators gathered on a representative sample of 2,532 elderly Americans, all hospitalized in a particular time window with pneumonia as their principal diagnosis. And this was the original RAND benefit-only scale, the one that my colleague Emmett Keeler built back in the 1980s. He got the 83 variables down to a scale that only had 14 variables in it. And this table shows you those 14 variables. Even after adjusting for everything else that was available, it's interesting, the patient's age still came in as an important predictor of sickness. Age is actually proxying for other things that go wrong when you get old. And so if we had a really good sickness model, age would fall out. It would drop out as not being useful after all the other stuff was in there. And the fact that age still stuck around as a useful predictor was a way of saying that we hadn't really found all the sickness indicators. It was proxying for the other sickness things. A person's systolic blood pressure matters. Whether their chest X-ray shows congestive heart failure. Blood urea nitrogen, anybody know about that? BUN? Do we have any medical people in the room? It's a measure of kidney functioning. And obviously, when you have pneumonia, you want to make sure things like your liver and your kidney are performing well. Kidneys are performing well. Prior to our work, people had created a score for measuring sickness that was intended to be used in emergency rooms. It was called the Apache 2 scale. And the total Apache score on a 36-point scale was the top variable there. And in fact, it was the single variable that was most strongly correlated with the binary outcome, death or not. So that column called correlation just gives the marginal correlation of each variable with the outcome. But it turned out that the Apache 2 people intended that scale to be used only in emergency rooms. Only for patients in the intensive care unit. And so it was necessary to reweight that scale for our patients. And one way to do that in regression is you put in the total score, and then you also put in all of the elements that go into the total score, and you see which ones turn out to be significant above and beyond the whole score. And that way, you will be able to reweight some of the elements of the scale. So it turned out the coma score inside Apache 2 needed different weighing. Serum albumin, I don't remember what that does clinically. It might, in fact, have something to do with liver function. Whether the patient was had shortness of breath is obviously relevant for pneumonia and respiratory distress. Septic complications is about blood poisoning, full body infection, naturally enough. Had you had a prior respiratory failure, clearly helps to predict whether you're going to do well with this pneumonia. Were you recently hospitalized for something else? And how strongly ambulatory were you before you got hospitalized? This was all elderly people. They were people who were on the Medicare system, 65 and over, and so some people in that age range don't get around very well in terms of walking, and so that was important. And interestingly, temperature is pretty important, and in the opposite direction than you might think. Temperature was negatively correlated with death. Can anybody make up a story for why that would be true with pneumonia? In other words, the higher your temperature upon admission to the hospital, the lower your chance of death within 30 days of admission. And the reason is that pneumonia is based on an infection, and a higher temperature means your body's responding to the infection and is fighting it. And so, yes, you want a higher temperature. Not too high, obviously, but you want a higher temperature than normal. So those were the variables that were in the RAND scale, and those are the costs, marginal cost per data collection in US dollars at the time in that column there. And you can see that some of the variables aren't necessarily that cost effective. The total Apache 2 score does have the highest marginal correlation with the outcome, but it costs by far the most of all the other variables because it takes so much time to measure all the different things that go into the scale. You pick a variable like systolic blood pressure, for example. It correlates rather strongly with the outcome, and yet it only costs 17 cents versus $3.33. So a variable like that will be particularly valuable in a cost-benefit sense because you give up a little bit of correlation, but you gain a lot of cost. And the column called good question mark turns out to show you which variables turned out to be in our final scale that we created from the cost-benefit approach. And it's interesting that Emmett did a good job in the sense that the only variables that showed up out of all 83, the only variables that showed up as useful from a cost-benefit point of view were a subset of these 14 variables. But in fact, we were able to show that you could save even more money by dropping 1, 2, 3, 4, 5, 6 of those variables in relation to what was done with them. Because it turns out that the hospitals around the country do not have a standard place in the medical record where the age variable is listed. You would like it to be true in medicine that every hospital in the country has the same exact system for recording data. But that is very much not true even today, and it was even worse in those days. It was a kind of Tower of Babel in which hospitals had vastly different ways of writing down the information about the patients. And some hospitals would bury the age information on page 12 of the medical record, and others would have it right there on page 1, and so on. So, yes, I can't tell you why that happened exactly. Oh, good. Oh, good. That's interesting. So you have two ways to infer the person's age: what they said and what their birth date was. What they say, yeah. Mhm. Yeah. And you could use their name. Yeah, I suppose. A person whose first name is Ebenezer is probably is older than a person whose first name is. Yeah, that's right. So, yeah. Okay. So you get the idea. And now we're going to try to do better. So here's how we're going to formulate this problem that will bring in a utility function in a useful way. So let's suppose the following. First of all, A, the 30-day mortality outcome, let's call it Y sub I, binary 1 for having died within 30 days of admission, 0 if lived, and data on P sickness indicators, XI1 through XIP. Those data values have been collected on little n individuals, sampled exchangeably from a population script P of patients with a given disease. And also B, the goal is to predict the death outcome for n star new patients who will in the future be sampled exchangeably from P. C, and to do so on the basis of some or all of the predictors, X1 through XP, when D, the marginal costs of data collection per patient, let's call those numbers C1 through CP, for the X's vary considerably. So that's the way we formulated the problem. The question then becomes, what is the best subset of the XJs to choose if a fixed amount of money is available for this task and you're rewarded based on the quality of your predictions? So right away there's a problem because you're asking what's going to happen on new patients, and you haven't seen them yet. By definition, they're new. They haven't arrived yet. So what you can do is a form of cross-validation on your existing data. You can sample, you can divide again. This is not for the purpose of model comparison, but it's for the purpose of proxying for future data. you can partition the existing data into modeling and validation subsets and use the validation subset as a proxy for future data. So we'll put n sub m observations in the modeling subsample, and we'll build our mortality predictions with that data set, and then we'll put the rest of them, n sub v observations, into the validation subsample, and that will serve as a proxy for the future. Now, the thing that's the most difficult about any decision theoretic problem is that you have to be able to combine all the costs and benefits of a particular action on a single numerical scale. And because cost comes naturally on a money scale, for example, US dollars, the most natural thing to do is to take all the benefits and translate them to the dollar scale as well. And that way you're combining apples with apples. But of course, that's the rub. That's the hard part of implementing this, because somehow you have to be able to measure the monetary value of a benefit in a problem that has a health context to it. And that's always potentially a difficult thing to do. And it brings in issues that we talked about many weeks ago involving the monetary value of human life and the monetary value of particular degradations to human life, like having been in a coma for a while and then having recovered from the coma but having lost some of your function, for example. These all sound like difficult and squirmy things to talk about, and we actually found a way to not have to go down to that level of things that made good sense and worked well. But somehow, benefit has to come out on the money scale the same way that cost does. Well, the data collection part's easy. We want cost to be small, so we want minus cost to be large, and so whenever utility is always supposed to be big, and so the data collection part of the utility function is just the negative of the total amount of money required to gather the data on a specific predictor subset. So that's easy to quantify as in equation 1 right there on page 6. Let's let ij be 1 if variable j is included in a given model and 0 otherwise. Then the data collection utility associated with a particular subset, I1 through IP, of the variables for patients in the validation subsample, well, you take a weighted sum of the CJs times the IJs. Of course, whenever a variable's not in there, that product is 0, and when it is in there, it gets a cost of CJ. And you add that up across all the predictor variables, and since you're going to apply the same model to all the patients in the validation subset, you just multiply that sum by how many patients there are in that subset and hit it with a minus sign, and that's going to be your utility for negative loss, you might say, for data collection cost. So that part was really easy, and the other part is the hard bit, and I'll just skip over it and come back to it in a moment and say that once we solve the hard bit, I'm going to call that part U sub D for data collection of the indicator vector. Then the hard part, we're going to solve it eventually, and we're going to get a predictive part, U sub P of I, which represents predictive reward, and then we simply add those two things together. So in equation 5, we're going to be maximizing expected utility, which is formed by simply adding those two things together. In other words, we could have gone through a further attempt to apply weights in front of the data collection utility and the predictive accuracy utility, but we had a reason for not doing that. So once we get this thing called UP of I, by some means, we can then simply combine it in an additive fashion with UD of I. That becomes our utility function, U of I. And the action space clearly here is the set of all possible subsets of the predictors, just as it was earlier when we were doing those BMA and BMS calculations. And so any element, any action, little a in that space, script A, is simply one of these indicator vectors that says which variables are in the model and which are not, with ones and zeros. And then we have to take the expectation. But how did we get this predictive benefit part? Like it says at the bottom of page 6, to measure the accuracy of a model's predictions, a metric is needed that quantifies the discrepancy between the actual and predicted values. And in this problem, the metric must come out in monetary terms on a scale that's comparable to that employed with the data collection utility. All right, well, in this setting of this problem anyway, the outcome yi, the outcomes are binary death indicators, and the logistic regression process is going to give a predicted death probability for each patient PI had. And so now somehow we need to compare the ones and zeros with the p hats and reward ourselves if the p hats are close to the ones and zeros, and penalize ourselves if they're not. So we used an approach to the comparison of actual and predicted values that dichotomized the p hats with respect to a cutoff. And the reason we did that was we were trying to mimic the decision-making reality that actions taken on the basis of this sort of observed versus expected qualities that have an all or nothing character at the hospital. A much more expensive and intensive audit of what's going on in the hospital or not. So eventually there's an all or nothing decision there, and we decided to mimic that all or nothing character by comparing the ones zeros with the p hats in using a rule that broke things at a cutoff. In other words, we're going to predict someone dies if the pi hat value is bigger than some cutoff c, and otherwise we're going to predict that they don't die. And what you would do if you ran a more expensive and more detailed audit is you would have to go in and look not only at the outcomes of care and the sickness of the patients, but you'd have to begin looking at the processes of care. You'd have to decide whether standard protocols for treating pneumonia patients were actually met on a frequent basis inside this hospital or not, and such protocols have been developed already. In fact, our study, the RAND study, was one of the first studies in the history of medicine in the world, really, to create such protocols in a quite systematic way. So here's how we go. We're going to now create these p hats and compare them with the ones and zeros with a cutoff. So in the first step of our approach, given a particular predictor subset, we fit a logistic regression model to the modeling subsample M in using only the predictor variables in that particular subset, and then we applied that model to the validation subsample V to create predicted death probabilities. And so in more detail, just reminding you of the details of a logistic regression model, again, letting yi be 1 if patient I dies within the 30-day window and 0 otherwise. Let's have xi1 through xik be the k sickness predictors for this particular patient under model I. The logistic regression model looks like what you see right there in equation 2 on page 8. Everybody has their own probability of dying initially. So yi given pi indexed by the variable set capital I. Those guys behave like independent Bernoulli draws where everybody has their own p, chance of dying. And then that model, like so many of our models, starts out scientifically promising in that you do want to have flexibility to let everybody have their own chance of dying, but that's too many parameters. We have n observations and n parameters, so we drop down from n parameters down to a much smaller number here by fitting a regression in which the probabilities are related linearly to the available predictor variables x1 through xk. The right-hand side, because the betas can live anywhere they want on the real line, and so can most of the x's anyway, the right-hand side of that equal sign in the second line down lives on the whole real line. And if I just tried to make a regression of the pi's on that, we'd have a mismatch between where those values live, because probabilities can only live on the interval from 0 to 1. And so somehow we have to make a transformation of the pi's so that that transformed version of them lives on the whole real line in order to be able to match up the left-hand side with the right-hand side. And that's what the thing called the logit of pi does on the left-hand side, where the logit, L-O-G-I-T, of pi is defined to be the logarithm of the odds ratio. Because if you start with pi that lives between 0 and 1 and compute the odds from it, pi over 1 minus pi, now the odds live between 0 and plus infinity, and then by taking the log of a positive number, we now have values that live anywhere they want on the whole real line. So it makes pretty good sense. And we used maximum likelihood to fit this model as a computationally efficient shortcut for Bayesian fitting with diffuse priors. That gives us a vector beta hat of estimated logistic regression coefficients. And then we apply those regression coefficients to all the patients in the subsample. the usual formula that you get by solving the bottom equation in item 2 on the top of this page backwards for the pi hat is that they are related to the betas and the x's through the equation you see there, 1 over 1 plus e to the minus the sum of beta hats times the x's. In an x0i as a vector of 1s, which will pick up the intercept. What's nice about this is that the pi hats themselves are numbers that represent a sickness score for that patient. In fact, most work that people do, and we still do this at Kaiser these days, we build models like logistic regressions where the outcome is death and the predictors are various measures of sickness. And when we're done, the pi hats represent the actual sickness score. And it comes out on a probability scale. Someone with a pi hat of 0.8 is really, really sick because they have an 80% chance, a predicted 80% chance of dying within the next 30 days. That's a really bad sickness score. Someone whose pi hat is only 0.007, they're going to be fine, probably. So that's the first part. We get p hats for everybody, deriving the coefficients from the modeling part, and then applying the prediction equations to the validation part. And then in the second step of our approach, we classify patient I in the validation subsample as predicted dead or alive according to whether that person's p hat value is bigger than or smaller than a cutoff p star. And we choose the cutoff p star to maximize the predictive accuracy of that particular model by searching on a discrete grid from 0.01 to 0.99 by steps of 0.01. So we're giving each model its best chance of doing good predictions. And when we're done with that, we're able to cross-tabulate for each patient that person's actual death status against their predicted death status. And you could put actual and predicted on either the rows or the columns of that table. We chose in this illustration here to put actual on the rows and predicted on the columns. And so we can count how many patients C11 were predicted to die and actually did die. How many patients C12 were predicted to live but died? How many patients C21 were predicted to die but live? And how many patients C22 were predicted to live and did live? Those four numbers, C1, C11, C12, C21, and C22, have to add up to how many total patients there are in the validation sample, because everybody has to fall in one and only one cell of that table. And actually, I've been telling you the wrong numbers. Those things are the counts in the right-hand table there, N11, N12, N21, and N22. The C11 and C2 and C12 and so on are the costs associated with each of those things occurring. And so we will now create a very simple predictive utility in which we say, well, they should really have been called benefits. I guess we should have called them B11, B12, B21, and B22 for benefits. But in the notation I'm using here, to get the overall utility across all patients in the validation sample, you now multiply N11 of the patients have a reward associated with them of C11. So you multiply those things together and do the same thing across all four entries in the table. And when you're done, you have that predictive utility, UP of I. And there are details in the paper I just showed you. If you want to look at that paper, there are details on how we chose. Let's see, where is that? That's not what I want anymore. That's lecture note 5. I guess I forgot to download it, or perhaps I got rid of it already. Anyway, if you go back to the paper that we published in JASA and look through it, there's a whole section in which we talk about how we chose those weights, C11, C12, C21, and C22. Basically, we looked ahead to what would happen if a costly process audit was actually necessary. Clearly, if you think about it, C11 and C22 were the rewards down the diagonal for getting it right. Those should be positive numbers. And C12 and C21 are penalties, one of which is a penalty for a false prediction of living, and the other one a penalty for a false prediction of death. And we used a method that people call anchoring in the utility elicitation literature. Item 2 now, it says on this page from the JASA paper, says, because it's easier to correctly predict that a person lives than dies with these data, and that's because the overall pneumonia 30-day death rate in our sample was 16%. So that number is so small that if you just predicted that everybody lived, your prediction model would be correct about 84% of the time. That means that C11 is bigger than C22 because it's harder to predict which people are going to die than to say who's going to live, because almost everybody's going to live. Then it's arguably worse to, and this is the same false positive, false negative thing we've been talking about on and off for weeks now, it's arguably worse to label a bad hospital good than the other way around, because if a hospital really is bad and you don't find it, then bad care is going to continue at that hospital. Whereas if you label a good hospital bad, then you're going to make them go through an unnecessary process audit, and that will cost money, but it won't cost lives. So a bad labeling a bad hospital good is worse than the other way around, so you should take the absolute value of C12 to be bigger than that of C21. And moreover, it's natural that the magnitudes of the penalties should exceed those of the rewards, because the downside of this stuff is much worse than the upside. And so we then completed the utility specification by eliciting information from health experts in the US and UK, and we did it by first anchoring that cost C21 to the cost of subjecting a good hospital to an unnecessary process audit, and then we were able to elicit ratios from the experts relating the other CIJ values in the table to that number C21, and that gave us the remaining costs, or those C weights, capital C weights. So that's how we did the elicitation. It was not easy, but when we were done, we had a story where we understood what we had, and we were able to go about the business of maximizing expected utility. Actually, I do give more details right here. We got the vector that you see right there on the partway down page 10. The negatives are for the off-diagonal entries, and the positives are the diagonal entries. And the downside, the mistakes, are more costly than the successes, and so we eventually got C21 from the experts, and then everything else came out as multiples of ratios in relation to that. And then we did in a previous paper, we did a big sensitivity analysis on the choice of those numbers, and that demonstrated broad sensitivity of our findings to the, broad stability of our findings when the utility values were perturbed in sensible ways. Yes, please? That's correct. In other words, we gave each predictor subset its best chance of doing a good job of predicting the accuracy part of things. And so we used that. We were trying to create both a dichotomous outcome, which is the only outcome we have, and a dichotomous predicted outcome. And in fact, there are other ways to compare a dichotomous outcome with a continuous predicted outcome that we did not explore here. We just created a dichotomized predicted outcome and then cross-tabulated themselves, those two variables against each other. No. Like it says at the bottom of this page 8, every single model was allowed to find its own P star, which was simply chosen to be the one that created the best predictive accuracy in the validation sample of all the different cut points from 0.01 to 0.99. And the P stars changed from one model to another, but that's okay. We're giving every model the biggest chance of doing well. And now that they all have the biggest chance of doing well, we can compare them against each other and how well they do. Because you have to weigh the costs against the benefits. And the costs are clearly quantified through this equation 1. Do you buy that part of things? And now we have to come up with a number on the dollar scale that represents benefit of accurate prediction. And so having built this little table here, you want those numbers N11 and N22, the counts of what happened where you got it right, you want those counts to be large, and you want the counts off the diagonal to be small. And then you have to have one final round of judgment about what are the consequences of predicting a patient will die and finding out the patient actually died. That's going to be a positive net consequence for you, versus the N12 number and the C12 number that goes along with it. You suffer a cost in that regard. You are penalized for having predicted that someone lived when in fact they died. And indeed that particular mistake is worse than the other one from a point of view of understanding what's going on for quality of care. We have a utility function that involves a simple additive combination of the data collection cost with a minus sign in front of it, right there in equation 1. Then we create a number on the dollar scale that corresponds to how accurately each model created predictions in the validation subsample. That's that item 4. And now we simply combine them by adding the two. So data collection cost is hidden, or not hidden, but it's quantified solely in that term U sub D of I. And predictive accuracy is quantified solely through this term UP of I, predictive utility of I. And the predictive utility of I has to have some positive costs and some positive weights and some negative weights in it, because 2 of the possibilities are correct and the other 2 are incorrect. So those numbers C11, C12, C21, and C22 have to be a mixture of plus and minus numbers. And in fact, using those basic rules I suggested to you a minute ago, the biggest number for the worst thing that can happen is the cell that I just mentioned before. That's the cell in which you predict a patient lives and actually they die. That's an example of quite bad quality of care. So the minus 139.2 has the biggest absolute value. It has to have a negative sign in front of it because it's a mistake. And the other one was judged by the experts to be only about half that bad. So half of 139.2 is 69.8. And so on. The other numbers were related to the 139.2 by ratios that we elicited from experts. And I see now that it's time for our next break. So VC Ops will shut things off now for 15 minutes and start again at 2:45. So here we are, having built this utility function. And now the question is, as follows. We are told by Frank Ramsey all those decades ago that we should not try to maximize utility because we can't, because it involves things we don't know. Instead, we should try to maximize expected utility, where the expectation is over your uncertainty about the things you don't know. And the principal thing we don't know here is how the future patients will behave. And so the expectation in equation 5 is over all possible cross-validation splits of the data. And so what we're going to be doing to approximate that expectation is repeatedly dividing our data set into, partitioning our data set into modeling and validation subsamples, do that a lot, and get the utility each time and calculate the expected utility averaging over those cross-validation splits. Well, here are some results. First of all, the number of possible cross-validation splits is far too large to do full enumeration on it, so we use Monte Carlo. We simply create capital N random modeling and validation splits and average over those, and try to make capital N big enough to have the Monte Carlo standard error of the expected utility be small enough to we made capital N big enough so that it was on the order of a penny on the scale of dollars, and that was accurate enough to see what's going on. So to see how well this works, we did two things, or actually I should say to see how well various methods of searching in this space worked. We created two worlds. We called one of them a small world, the other one a big world. The small world has the advantage that if we focus on a small enough set of possible subsets, we can actually do complete brute force enumeration of the expected utility of all models, and we can therefore try various optimization methods with a small amount of CPU time to see how well they actually recover the best models, because we know which ones the best models are. So 2 to the 14th is only 16,384 models to look at. And 14 is, of course, the number that was the number of variables in the RAND scale that we were trying to improve upon. So a convenient way to create a small world was to regard those 14 variables as defining the full space of models that we had available to ourselves for the, rather, full space of predictors that we had available to ourselves for creating the small world. And then we did brute force enumeration across all 16,384 models. This was about 10 years ago, and computers weren't that fast. And so, in fact, the brute force enumeration of all those estimated expected utilities took about 3 months on the computers that we had available to us. But we did it, and then we had the truth. And then we could begin running experiments in which we could see how close we could get to the truth by taking each of a variety of stochastic optimization techniques, simulated annealing or genetic algorithms or taboo search, and providing each of them with a quite small budget of CPU time, and then seeing how well each one of them did at finding the best models. And this is a world in which we know what the best models are. Then we tried to turn the methods loose in the big world, defined by all 83 available predictors. And as I said before, 2 to the 83rd is about 10 to the 25th, and we can't possibly do brute force enumeration there. So we just did our best. Basically, we looked around for subsets that appeared to be good on the basis of a series of very long runs that gave us a sense of where the good models were, and then we looked to see how well these different stochastic optimization methods came to recovering truth. One of the main messages from our study is captured in a single figure, which I like very much, and here I believe it is. This picture is called parallel box plots. Each of the vertical things in this diagram is something called a box plot. This is a device that was invented by John Tukey, the guy who developed various exploratory data analysis methods. His idea was to create a graphical summary of a column of numbers that would draw your attention to a large number of its salient features in a small amount of graphical space. So the center of these pictures is called the box, and the little dots that are going out of the box, in this case in a vertical and horizontal direction, are called the whiskers. And so sometimes these pictures, instead of being called box plots, are called box and whisker plots. The left and right edges of the box, which in this picture, because box plots are usually plotted, rotated 90 degrees from this here, I'll just say it in this context. The top and bottom edges of the box in the middle are defined to be the 25th percentile and the 75th percentile of the distribution of numbers. And the horizontal white bar in the middle of each of the boxes is the median, the 50th percentile. Then the whiskers are supposed to go out to a point that defines the outer limit of what the normal curve would have expected with the same sample size as the number of observations in that particular sample. And anything beyond that point, those points are defined by those things that look like square brackets on rotated 90 degrees, open and closed square brackets. Anything beyond that point is regarded by the normal distribution as a potential outlier, And in this particular way of plotting them, the outliers are all drawn as horizontal lines where several of them close to each other would correspond to creating a thick horizontal line. There's one column in this picture for each total number of variables in the model. And the vertical scale in this picture is the estimated expected utility. So at the left edge of this picture, we have someone who says, I'm going to try to save money by not using any predictor variables at all. And of course, that has the advantage of not costing any data collection costs at all. That's great from that point of view. But it also predicts very badly. And when you weigh them against each other, you find that it has an estimated, there's only one model that has no predictors in it at all. It has an estimated expected utility of about negative $14.50. At the other extreme, we have the RAND scale, which used all 14 variables. And with only 14 variables available, 14 choose 14 is 1. There's only one particular model that has all 14 of them in it. And it does a good job of predicting, but because it has variables in it that are unnecessary, it costs too much relative to how well it predicts. And so actually, in the expected utility calculation that we did, the model with all 14 predictors is worse than the one in which you ignore all the variables completely and just say that everybody has an 16% chance of dying. Worse by about 50 cents, not that much in it. But what's lovely about this picture is that if you start tracking the medians of those bars, they have a lovely bowl-shaped down concave character to them. In other words, one variable in the model, the next one over are the expected utility values of all the different models that have only one variable in them. There would be 14 such models, of course. Then the next one over has all the estimated expected utilities of the people who, or rather the models that had 2 predictors in them. And 14 choose 2 is 14 times 13 over 2. 7 times 13 is about 91. Did I get that right? So there's 91 models there, and so on. And what you see is this nice thing happening where as you increase variables for a while, there's a monotonic improvement, and then it goes down again. Moreover, the medians aren't really that interesting. What we really care about is the models that do the very best. And so you want to look at the very upper edge of each of these box plots and look around for the very best models. And you can see that they're all concentrated around 4, 5, or 6 predictors. And so the 20 best models, it turns out, included the same 3 variables 18 or more times out of 20, and never included 6 of the other variables. They just completely got dropped out of the 14 variables there. The 5 best models, it turns out, were minor variations on each other and included between 4 and 6 variables. And so the last column back on that, in that table back here, shows you these are the 1, 2, 3, 4, 5, 6, 7, 8 variables that occurred the most often in the 20 best models, and the ones with the double stars defined the very best model of all from a cost-benefit point of view. That, in fact, only has 1, 2, 3, 4 variables in it. All 4 of them are relatively cheap, and if you look at them, they manage to achieve a good compromise between cheapness on the one hand and predictive signal marginally on the other hand. And the best models, if you look at them, save almost $8 per patient over the full 14-variable model. So I can compare the lower right-hand corner and see how much better those are doing. We're at about minus $15 for the full model and at about minus $8 for the other. So I guess I would say that's actually about $7 per patient. And of course, this would amount to a significant savings if it were aggregated across many patients, as it would be if it were done on a routine basis. In fact, the time it took from when this study was done until we came out, the RAND study was done until we came out with this study, in that time, we were overtaken by events because by now people have electronic medical records to an increasing degree, and so the marginal cost of each of the variables is essentially 0 now. not quite, but those marginal costs are now being absorbed into the routine work that the nurses do when they go around on their rounds and take vital signs, for example, and type them into the terminals next to people's bedsides. So I am not able to say that this approach has been used widely, although it's potentially widely usable in parts of the world that don't have electronic medical records yet. And I have not gone out of my way to try to bang the drum to make that happen, but in principle, this approach could be used not just in medicine, but in all manner of settings in which you're trying to build a scale that measures something like sickness or some other thing. Another realm in which this occurs is when you're trying to create a scale that measures how likely someone will be to default on a loan, for example, and the kinds of variables that you use to predict whether the person is going to default or not may indeed cost different amounts of money because they have to be bought from different databases, for example. And so you get a chunk of variables from one database. Perhaps you could regard all of them costing the same because you have to pay one fixed cost to get all the data in that database, and you get a chunk of other variables from another data source. So this could be used without any trouble in credit scoring. And I bet there are people in the room today who have other scoring problems where you're trying to create a score that predicts how likely it is that someone will click on something, for example. And it may turn out in your world that the actual cost of the input to get those particular features or X variables or predictors might for some reason differ in your realm as you go from one predictor variable to another. And if that's true, this technology could be helpful to you. Yeah, that's right. When the marginal cost per variable is relatively high, and especially when some variables have a noticeably higher marginal cost than other ones. If the ratio of highest marginal cost to lowest is no bigger than, let's say, 1.5 to 1, then you probably wouldn't get a lot of bang from this compared with ordinary benefit-only calculations. But in our problem, it ranged all the way up to $3.33 and all the way down to 17 cents, and that's a big ratio. That's a ratio of about 20, isn't it? So it mattered quite a bit. So I won't say too much about approach 2 because it's off the main line and it's more mathematical. You can read it at your own convenience. But I do want to make a point that is described here on page 13. Maximizing expected utility, as I've written here, as in the approach I just showed you, is a natural Bayesian way forward in this problem. And I will note that it does solve the problem that I posed for us a while ago, namely to do model comparison in a way that's driven by utility, by actually making a decision. It's a hard thing to do, but it can be done, and there you saw it done. It's a natural way forward, but there's two things. Firstly, the elicitation process was complicated and difficult. And secondly, the utility structure we examined was only one of a number of plausible alternatives, and several gentlemen in the room here have suggested to me an alternative already today, which would have been interesting to compare with this. And the main problem is that utility is framed from only one point of view. And so the broader question for a decision theoretic approach is whose utility? Whose ox is gored here? Whose utility should drive this? There's a nasty theorem that Ken Arrow proved a long time ago that says it's called Arrow's impossibility theorem, and it says that essentially anytime two or more people are trying to make a decision together in settings of partial cooperation and partial competition, there is no guarantee that they will be able to find a way forward that makes them both maximally happy. And the Bayesian statistician Jay Cadane has a theorem that follows behind Arrow's theorem that says, in fact, if two Bayesians are trying to make a decision together, then they first of all have to agree on the action space. And then secondly, the only way they can jointly agree is if either their utility functions coincide or their probabilities precisely coincide. And that will generally not be true. So, and this problem provides a really good test bed for thinking these issues through. Think about the quality of care issue and how many different people there are who are actors in the drama or stakeholders. There's patients whose utility function tends to be of the form, I think I may have mentioned this before, when there's something wrong with me, I want the system to spend infinity dollars on me right now, right? That's how most of us behave. Although those of us who are a little more charitable would say, I want the system to spend almost infinity dollars on me soon, but I recognize that if it spends nearly infinity dollars on me, that will not leave enough for you when you get sick, and so maybe I do want to hold back my own enthusiasm for spending the healthcare system's money a little so that some is left over for you, where you is a generic other person, for example. Even so, that person's utility function is going to be different from that with respect to measuring quality of care. That person's utility function, how much should we spend to measure quality of care, for example? This is an interesting question that no one has answered in a principled way yet. The part of the government that runs Medicare is called, anybody in here ever worked with them before? It's called the Centers for Medicare and Medicaid Services, and it should be called CMMS for that reason, because it has two M's in it, but for some reason they call themselves CMS, as though the M only occurred once. And they have to decide every year how much of their budget should be spent on measuring how well hospitals are treating Medicare patients, and how much of the budget should be spent on actually treating. And that's a really interesting question, because obviously at either extreme, you're in the wrong place. If you don't spend any money on measuring quality, then people will start to cut corners because they notice they aren't being watched at all. If you spend every single dollar on measuring quality, then there's no money left over to treat people. So, as is so true in life with so many things, bad at one end of the scale, bad at the other end of the scale, Goldilocks and the Three Bears, right? There's some sweet spot in the middle. How do we find the sweet spot, the optimal amount of money to spend on measuring quality of care in order to promote higher quality of care? And that would involve weighing a whole bunch of different stakeholders' utility functions in there. Patients largely want the money spent on them, and so they don't want much money spent on quality because they think that the system's already pretty good and they just want the doctors to do the expensive things for them to get them well. The doctors have different utility functions because people are looking over their shoulders all the time. Some doctors I know would rather that not much money was spent on quality measurement at all, because that would mean they don't have to be bothered by these quality people looking over their shoulders, but that's probably not the right attitude. The hospital administrators have yet a different utility structure. The regulators at the state level and the regulators at the federal level, everybody has a different set of things that they care about in this big drama. And we do not yet have a principled way to come to a consensus for how this should be resolved. I believe the way CMMS does this is that to decide how much they should spend on measuring quality next year, they look at how much they spent on measuring quality this year, and they take that number and adjust it up or down by some small, multiplied by 1.0x, 1 plus epsilon, where epsilon is either a little bit bigger than 0 or a little bit smaller than 0. So many systems do that, right? If you watch how people make decisions about how to spend money, you pretend that what you did last year was great, and then you do tiny changes to the thing that you pretend is great at the margin instead of thinking the problem through carefully. And really bad choices end up getting made that way. The UC system has just gone through a process attempting to recover from a mistake of that kind. Did you know, maybe some of you have kids or had kids or will have kids that go to branches of the UC system, did you know that it's not the case that the UC Office of the President pays every campus of the UC system the same amount of money for each student? Because of a weird historical system that's based upon making tiny changes at the margin over a long period of time, Campuses like Berkeley and UCLA are paid a lot more per student than campuses like Santa Cruz and Riverside and Davis and Santa Barbara and Irvine and so on, the smaller campuses. Finally, it was brought to the president of the UC system's attention that this was true, and it was gently suggested to him that there was no reason why that should be so, and in fact, principles of fairness would dictate that every school should be paid the same amount. And so they're doing a process now called rebenching, in which they're trying to spread the money around in a way that's closer to the goal of equality and fairness. And of course, that's goring the oxes of the Berkeley and UCLA campuses because, in effect, they're going to be redistributing wealth away from those campuses that had an incorrect historical advantage to the campuses that were being incorrectly disadvantaged. And it's all because over a 30-year period, they just took something that might have been okay 30 years ago and just changed it 1% up or down every year from that point on. And eventually you get to something that's really absurd by doing it. Every 5 or 10 years with a system like that, you have to stop and clear it out completely and start over again based upon some decent principles. And then you can go along changing at the margin for 5 or 10 more years, but then you have to stop and do it over again, basically. That's practically the only way you can go forward. So this is a hard problem. There is no solution to this problem in general. In fact, the last word to be said about decision making, optimal decision making in this story, is that everything I've told you about how to make optimal decisions through maximizing expected utility assumes implicitly that there is one and only one utility function that needs to have its expectation maximized. And that obviously applies directly to individuals, provided they can figure out what their utility functions are. And it also applies to collectives as long as everybody in the collective agrees on the same utility function. So one way to do that would be to appoint someone in your collective the czar, and each of you lobbies the czar for the things that ought to be in the utility function, and then we all submit to the will of the czar who announces what our collective utility function is. In some informal sense, that's how corporations run. Because there's I'm consulting for eBay these days. eBay either has or ought to have a corporate utility function. It is, to the extent that it's there, it's being driven, at least in some part, or should be being driven by the vision, the vision of the CEO, for example. And so that's like eBay having elected a czar. And basically, big changes occur inside companies every now and then when a new CEO comes in and says, we're going to do things really differently. That's an example of that. You've elected a czar. That person has a utility function which gets imposed on everybody from that point on. I've already noticed inside eBay, and I bet that's true in every organization for every person in the room, that in fact, lots of people are behaving inside eBay as though their own personal utility function, when you stare at it, probably runs counter to the corporate utility function in various ways. We are not all rowing in the same direction in this organization, nor are you and all the people in your organization either, I bet. And this has been arrived at by putting in incentives to try to make things better, but the incentives turn out to have perverse consequences around the edges, and so people end up doing things to get bigger bonuses that may not actually be good for the company overall, right? That happens probably in any structure where behavior is incentivized with money. So, hard problem, no one knows the answer to it. This is the big limitation of optimal decision making. It only works when there's a single utility function that either is there because there's one person who has it, or it's there because you as a collective have somehow come up with one utility function, either by electing a czar or by some other means. Somehow, magically, everybody in the little collective all agrees on the same utility function. That doesn't happen that often, but I suppose it could. Not much work in economics or statistics on how to come up with a compromise story that comes as close as possible to sort of satisfying everybody. So you have to make mathematical the idea of close and sort of, right? And I'm not aware of much work along those lines, but maybe that's just because I'm not aware of it. Hmm. Right, right. But those words have the flavor of what I'm thinking of. Have you ever heard the verb to satisfice? It means you don't get exactly what you want, but we hope you get something kind of near what you want. You aren't completely satisfied, but you have been satisficed. um, and so that's what we're trying to do in a situation like that. We're trying to make everybody come out of the process feeling like they got somewhere close to what they really wanted to have happen. The American voting system is like this, right? Everybody has different utilities about what to do in the political system, and yet every 4 years we make a giant dichotomous choice. And so is there a better way to do it than the way we do it now that comes closer to satisfying everybody in the country? It's a good question to think about while you're taking a shower sometime. Okay, so the rest of this I'm just going to leave to you because I want to tell you, instead of telling you about cost-adjusted BIC, I want to tell you about BIC itself, the basic thing that we were in the process of trying to improve upon. So let's go back to the main line here. So I just showed you how to do it, but I think you saw also that it's hard. So like it says here on page 45 of part 5 of the main lecture notes, this is hard work, and there's a powerful desire for generic model comparison methods. And you can hope that you can find such a method that has the property that its utility structure may provide a decent approximation to what you would have gotten if you spent all that effort to really do it right. And 2 methods have been developed so far that have at least the veneer of utility over top of them as Bayesian model comparison methods. One is called Bayes factors, and the other one is these log score things I've been mentioning. So let me tell you the Bayes factor story, which is interesting and difficult. It sure looks natural, like we were seeing was done in the BMA and BMS code to compare models on the basis of their posterior probabilities, right? If you've got a bunch of models, you can ask the data what the posterior probability is that the data generating mechanism was this one rather than that one, for example. And so if you write down Bayes' theorem in odds form, you get equation 8 at the top of page 46. And the left-hand side says the posterior odds in favor of model 2 over model 1 in a comparison where model 1 and model 2 are the only things in the universe, then it has to be P over 1 minus P, so it would be odds. Or you could talk about it as, yeah, that's a good way to talk about it. So the left-hand side is the posterior odds in favor of model 2 over model 1. And then you can break down the right-hand side into the product of 2 things, the first term of which is the prior odds in favor of model 2 over model 1, and the other one is the thing that earlier in the course when we talked about ELISA we called the Bayes factor. It's a relative comparison of how plausible the data is under model 2 versus how plausible the data is under model 1. And that certainly seems like it's pretty reasonable. So in words, equation 8 says posterior odds for model 2 over model 1 equals prior odds for model 2 over model 1 times Bayes factor for model 2 over model 1. It looks like the Bayes factor idea goes back to World War II and was invented by Alan Turing and Jack Good working together on the project that tried to crack the German Enigma codes. It seems to be they were the first people to think this through and try to use it in a real problem. They didn't call them Bayes factors then, but that's what they were doing. And you remember that odds, little o, are related to probabilities, little p, via o equals p over 1 minus p, and we can solve that backwards and get p equals o over 1 plus o. And these are both monotone increasing transformations. So here's 2 decision rules. Choose M2 over M1 if the posterior odds for M2 are greater. Here's decision rule 2. Choose M2 over M1 if the posterior probability of M2 is bigger than the posterior probability of M1. Those are equivalent. So that suggests why not say one model is better than another if it has a bigger posterior model probability. That would be a reasonable sounding thing to do. However, to compute that, you have to be prepared to take a position on prior odds. You see it right there in equation 8, right? So you have to not only, it's going to turn out you have to not only put priors on the parameters inside each model, you have to put a prior on the plausibility of the models to begin with. And that doesn't sound like that easy a thing to do. People have tried priors based upon this thing called Occam's razor. Anybody heard that phrase before? It basically just says that unless you have compelling reason to do otherwise, simple things are better than complicated things, right? That's one way to rephrase it. And so you could try penalizing models in their prior probabilities based upon how complex they seem, on the ground, the Occam's razor ground, that truth is. I guess that guy William of Ockham, the one who invented it, if he really did say this, he was sort of claiming, implicitly at least, that God or nature or whatever you want to call the process that led us to where we are now favors simple mechanisms over complicated ones. But is that really true based on what you've seen in your own life? I'm not sure that's true. We are certainly very delighted every time we find something that's pretty simple, like Newton's laws of gravitation and so on, but is that really a complete description of all things in the world anyway? So you can see there's a toughness right there. How do you set the prior model probabilities? What do you suppose? What's that? That's true. We put priors on sampling distributions, but we didn't have to actually face numerically the question of how much prior probability would you put on model 2 versus model 1. Well, that's right. The model averaging process basically started out giving them all equal weight, right? And that has to be the no-brainer thing to do if you're looking around for a no-brainer thing to do, because just set them all equal and then that factor disappears because it's 1, right? So you don't have to think about it anymore. So that's a popular choice, even though it isn't necessarily the best choice. A different choice would be in the variable selection approach to give more prior model probability to the simpler models and downweight the really, really complex ones. But that would be on the basis of what we are supposed to be, according to the thing I've been sharing with you this whole course. That's supposed to be based on prior information, not prior belief based upon William of Ockham having somehow had a good idea. I don't know. Anyway. If you try to force this into a decision theoretic basis, there is one, but it's rather odd, and here it is. You have to pretend that the only possible data generating mechanisms are M1 through MM in a finite set, script M. Then you further have to pretend that one of those models is the true data generating mechanism, M sub dg. And then after those two pretends, you pretend that the following utility function reflects your real world values. You give yourself a 1 if you get it right, and you give yourself nothing if you don't. And if you rub those three pretends together, then you can show that it's decision theoretically optimal to choose the model in script M with the highest posterior probability, because that choice maximizes expected utility. That's a lot of pretending, right? Even if you're prepared to believe, following the calibration principle, that there is some sort of true data generating mechanism, M sub dg, that's unknown to you in terms of its structure and then also in terms of its parameters hidden inside the structure and so on, are you really able to write down a set of models that you're prepared to make comparisons across that absolutely includes that data generating mechanism? You're sure somehow that it is in there. And moreover, that you only give yourself a reward if you get it exactly right. And it's one of those things where closeness only counts in horseshoes, my father used to say, right? Or what's another one like that? Closeness only counts in horseshoes and grenades, I think was another thing people used to say. But this is not that way. You get the prize if you get it exactly right, and you get nothing if you don't, even though you might have ended up with something that was very close in terms of its predictive consequences, for example. So, strange utility function, but there it is. Now, we aren't yet to Bayes factors because we still have to worry about those prior probabilities, because They are in there as well. So if it's scientifically appropriate to take the prior model probabilities to be equal, then finally this rule reduces to choosing the model with the highest Bayes factor in favor of it. And you can find this model by a series of pairwise comparisons. You first compute the Bayes factor in favor of model 2 over model 1, which is that ratio of the data plausibilities. And then you pick the one that's bigger of those two. And now let's call the better model M star. And now you compute the Bayes factor in favor of M star over some other model in your script M, and call the better model M star, and keep on doing that pairwise until you find the one that's the best. You can search any finite set by a series of binary comparisons amongst it. So, okay. Now, there's something else a bit funny about this, because look at that expression, P of D given MJ and B. It's your prior predictive distribution for the data set D under model J before the data set arrives. That's what it says to do. If you read it in Bayesian language and see what it says. It's not some kind of posterior predictive distribution. It's your prior predictive distribution. And so the Bayes factor rule tells you to choose the model that does the best job of predicting the data before any data arrive. Already that's kind of strange. And yet it's inexorably the thing that comes out of the logic of Bayes' theorem. It's just right there in front of you. So let's see how this would go. Suppose we are comparing a bunch of parametric models. Let's let model MJ have its own parameter vector, gamma j, of length kj. And across all these models, there's some quantity theta that's common to all of them, which might be expressible in terms of the parameter vector itself. And so we could decompose the gamma j into theta, the thing that we care about, and eta j, all the nuisance, so-called nuisance parameters. I won't dwell upon that part of things. But anyway, each model has its own parameter vector, and each model's parameter vector has its own length. So model J says, if you knew what gamma j was and you knew that model MJ was right, then your predictive distribution for D would follow the predictive distribution specific to those parameters in that model. That's the lower line of equation 12, what we would usually call the sampling distribution. And then you have to put a prior on the parameters as usual. And you'll note that the meaning of the parameters is specific to the particular model you're working with. So for example, and I think I've mentioned this to you before, we have a regression data set with a y variable and two x variables. And model 1, apart from the stochastics part of it in terms of all the details, says yi equals beta 0 plus beta 1 xi1 plus ei. And your impulse is to write down, if you're going to compare that with the model that has x2 in it, is to write down yi equals beta 0 plus beta 1 xi1 plus beta 2 xi2 plus ei. But what's wrong with that notationally? Pardon? The errors are definitely not the same. So we hope these errors are smaller. So this has to be plus epsilon I. Is it fixed now? The parameters are different. They have different meaning as well. Beta 1 in this model here represents the average effect of x1 on y, unadjusted for anything else. And beta 1 down here means the average effect of x1 on y after adjusting for the average effect of x2. And those are completely different things. So this really should be beta 0 prime plus beta 1 prime plus beta 2 prime plus epsilon. The y's, thank God, are the same, right? That part doesn't change. And the x's are the same, of course. But all the parameters really have to change their names because they mean something different in each model. And the error terms have to be different as well. Now, in this model, how do we get from the sampling distribution right there, P of D given gamma j, mj, and b, to the thing that we need in the Bayes factor? Well, the answer is you have to stick in the thing that you've got and then see what happens to relate it to what you want. And the answer is the equation 13. The thing we want in the numerator or denominator of the base factor is a weighted average of the things we have in the model, but look, weighted by the prior distribution on gamma j. And moreover, if model J has a parameter vector gamma j that has a lot of components in it, maybe think about one of these regression models where there's 56 things to choose from, and model J happens to have 26 or 27 predictor variables in it, so that vector has 27 or 28 parameters in it. That's a 27 or 28 dimensional integral that you have to compute to get the thing that's in the numerator of the base factor. So yet again, we now have a situation where something has arisen where we have to do a high dimensional integration to get something interesting to us. This is called an integrated likelihood or a marginal likelihood because it tells you to take a weighted average of the sampling distribution, which can often, as we know, be interpreted directly as the likelihood. But here's the strange part about it. You have to weight by the prior distribution or the parameters in model J. And as I said a second ago, this might seem quite surprising, but it's correct, and it can lead to trouble. Before I tell you the trouble it can lead to, I'll mention to you that there's an Australian guy called Murray Aitken who was so troubled by this that he said, in effect, I'm just going to tell you that I don't like equation 13. It has to be wrong. The thing that makes sense to me, feels right to me, is I should be taking the weighted average of the likelihood weighted by the posterior distribution on gamma j. And he called those things posterior Bayes factors. And he even managed to get a paper published on it that became a discussion paper in the Journal of the Royal Statistical Society Series B, which is one of the highest honors anyone can get in the entire statistics profession to have such a paper. And the entire idea is complete rubbish, because it has no basis whatsoever in probability. This is the right equation. We don't like it. I'm not happy about it, but this is the right equation. And what he was doing was trying to do something ad hoc and hope for the best. And the whole point of the Bayesian story is that you don't have to resort to ad hoc because there's one and only one way to behave. It's called Bayes' theorem and the things that flow from it. So if anybody ever mentions posterior Bayes factors, tell them politely to go do something impolite. It's just not the right thing to do. Now, as I said, the first trouble is technical. That integral can be difficult to compute, and it may not even be that easy to approximate. But the second thing to notice is that equation 13 is actually an expectation. Look at it. It's a weighted average of the sampling distribution weighted by the prior. And that's always an expectation of something. Namely, it's the expectation of the sampling distribution where the expectation is taken over the prior. And of course, we then evaluate that at the observed data set D. Now, we already know quite a bit about priors, but just to remind you, a distribution or density for a real valued parameter theta that summarizes the information. Theta is highly likely to be near theta 0. We'll have most of its mass concentrated near theta 0, whereas the information not much is known about theta would correspond to a density that's rather flat or diffuse across a broad range of theta values. So, as is often the case when scientific context offers little information about the gamma vector external to the data set D, this translates into a diffuse prior on the parameters, and that spells trouble for Bayes factors, because if you are going to take the expectation of something with respect to a diffuse prior, then imagine how unstable that's going to be. Suppose there was only a single gamma in this model, and it lived on the whole real line, and you put a diffuse prior on it by working with a uniform distribution from -1 million to +1 million. Now, I'm going to encourage you to use Monte Carlo to evaluate that expectation. What do? You take a draw from the prior, and then you stick in that number and evaluate P of D given that number and that particular model. Well, if the prior is uniform between -1 billion and +1 billion, where's the first draw going to land? Might land at +340 million. And you stick that number in there. Now go back and take another draw from the prior. The next time it might be at -219,000. Go ahead and stick that number in. Now take another draw. Next time it might be plus 486,000. In other words, how stable is that quantity when you're drawing numbers from a prior distribution that's uniform from minus a billion to plus a billion? The answer is it's all over the map. There's no sense of stability to it at all. So this is a real problem for Bayes factors. They are challenged by the very situation that comes up quite often, namely, not knowing much about the parameters inside the models will give rise to extreme instability of the ingredients, those marginal likelihood things or integrated likelihood things that go into the numerator and the denominator of the Bayes factor. Well, here's an example. I have an integer valued data set, D, which consists of the vector y1 through yn, and I'll take the mean and get y bar. Here's two different competing models for this vector of integers. This is not a realistic problem. This is a toy problem. I have never in my life had a real problem where I was confused between whether the sampling distribution was geometric or Poisson. But they both have the property that they live on the non-negative integers. And so model 1 says that the data are geometric with parameter theta 1. And I put a conjugate beta prior on theta 1. And model 2 says, oh no, the data is actually Poisson. The likelihood is Poisson with parameter theta 2, and I put a conjugate gamma prior on theta 2. After some unpleasant lifting, you can show that the Bayes factor has that hideous expression in equation 15 with a vast number of gamma functions that all have to be evaluated. Now let's start making the priors diffuse and see what happens. So there's a standard diffuse prior for theta 1, namely the uniform prior. Let's hold that constant and let the other prior be diffuse as a function of that number epsilon. Remember, we talked about these gamma epsilon epsilon priors. So go ahead and let it be a gamma epsilon epsilon prior, and let epsilon now be something that's just some small number positive. The Bayes factor now has the following simpler form, equation 16. And now look at this. That goes to plus infinity as epsilon goes to 0. In other words, you can make the evidence in favor of the geometric model over the Poisson as large as you want, no matter what the data says, as a function of this quantity epsilon in the prior near 0 that scientifically you have no basis to specify. Earlier this course I showed you people write down gamma epsilon epsilon priors, and sometimes they use 0.001, sometimes they use 0.01, sometimes they use 0.0001. There isn't any theory that tells you what the, quote, right epsilon is to use. And what this expression shows you is that you can make the Bayes factor in favor of the geometric model go to infinity just by making that number get smaller and smaller. And all of that is no matter what the data says. You completely ignore the data, and the Bayes factor goes to infinity as a function of something that does not have a unique scientific specification. And you can make it go the other way by doing the opposite thing. Let's fix and bound alpha 2 and beta 2 away from 0, and now let both alpha 1 and beta 1 go to 0, which is the way to make a very diffuse prior on the unit interval. Now we can completely reverse this and make the evidence in favor of the Poisson model over the geometric as large as you want. And again, that will be true no matter what the data says. So this is really embarrassing. And I hope that this hits you with the force that it should. Bayes factors are highly problematic in precisely the situation where you would want to use them on a regular basis, namely in settings where each model has a parameter vector and you don't know much about those parameters ahead of time. Because the things in the numerator and denominator that you're comparing with each other in the Bayes factor become extraordinarily unstable as a function of small details in how the diffuse priors are specified. Very embarrassing. So the bottom line is that when scientific context suggests diffuse priors on the parameter vectors in the models being compared, the integrated likelihood values that are at the heart of the Bayes factors can be hideously sensitive to small arbitrary details in how the diffuseness is specified. Now, people have known this for decades, and I think it's fair to say what I wrote here on this page. This has given rise to an amazing amount of fumbling around by Bayesians who are trying out one ad hoc thing after another. And this is in the middle of a paradigm where you aren't supposed to have to resort to ad hocery because there's meant to be only one way forward. Those three basic equations that we got out of Mr. Cox's theorem. And now we have this amazing list. We have partial Bayes factors, intrinsic Bayes factors, fractional Bayes factors, well-calibrated priors, conventional priors, intrinsic priors, expected posterior priors. The list just goes on and on. All of this exhibits a level of ad hocery that's otherwise absent from this paradigm. So Bayes factors are, it's like there's one place in your mouth that you don't try to go to very often because it hurts there. Bayes factors are that place in the Bayesian mouth. We don't, this is embarrassing for the paradigm. And I have to admit, bust yourself first, full disclosure, whatever you want to call it, that my student Fouskakis and his Greek friend and I are just right now trying to contribute to this literature in the context of variable selection by coming up with yet another improvement on this expected posterior prior idea. But we claim to be doing better than this because we claim that we have now finally found the way forward that removes all the ad hocery. We claim that. So at first I was embarrassed even to be working on this topic with my student because the whole thing is tainted by this ad hocery. But then as we found our solution, we began to realize that maybe what we really had was a small version of a holy grail where our approach really does remove all of the ad hocery. So I hope so. All right. If you buy into the Bayes factor story, and I'm about to suggest we do so for a little while to see that we can get to a place where this difficulty will go away. There's a phrase that goes something like, stop me before I harm myself again, or stop me before I kill again, or some phrase like that. There is going to be a little nugget of gold in the middle of this Bayes factor story. There's going to be a way to do something that has a strong Bayes factor flavor to it that keeps you from making this mistake of diffuseness leading to real instability. And to get there, we have to do a little bit of math. We want that integral. And that integral is going to be hard to compute. We're probably going to have to do either Markov chain Monte Carlo to estimate it, or we're going to have to do some sort of analytic thing to estimate it. And this is where Mr. Laplace, all the way back in 1770-something, already figured out what was the right thing to do with an integral like this. So he came up with an analytic approximation to this integral that we now call Laplace approximation. And the Laplace approximation leads the way out of this horrible morass and into a potential promised land. So here we go. He noticed, first of all, that the thing that we're trying to integrate, the thing to the right of the integral sign, is actually an unnormalized posterior distribution. Because look, it's a product of a prior and a sampling distribution. And so if we had the right normalizing constant in there, that thing would be a posterior distribution. And in fact, it's the unnormalized version of the posterior distribution for the parameter vector. He then appealed to a Bayesian version of the central limit theorem, which says that with a lot of data, such a posterior distribution should be close to Gaussian, centered at the posterior mode, which should be quite a lot like the maximum likelihood estimate if the prior information is diffuse. Then with a large sample size, because the thing we're trying to calculate is an unnormalized version of a Gaussian distribution, the logarithm of it should be close to a parabola, right? Because that's how you go e to the minus stuff that works like a parabola. Now you take the log of it, you're going to get a parabola, right? And so Laplace said to himself, that thing should be close to a quadratic around the mode. And so his idea, he already knew about Taylor series because the guy Taylor who invented it did his work about 60 years before Laplace came along. So Taylor series were right there in the mainstream of math, even though Taylor was a Brit and French didn't like to use British ideas in those days, and vice versa, by the way. But it was such a good idea that they had to use it because there it was, and they were, okay, fine, some British guy got there first, but okay, it's a good idea. So Laplace says, let's take a Taylor expansion of the logarithm of the integrand around the mode, and let's hold on to only the terms out to second order. And the result is equation 18. Look, the left-hand side is just what we want, except it's the logarithm of it. We want P of D given MJ and B. Laplace says, I'll give you a good approximation to the logarithm of that thing. And of course, then once you're done computing that, if you want it, just exponentiate. Well, look what's there. The first term on the right-hand side, let's think of gamma j hat as the maximum likelihood estimate of the parameter vector. That's going to be equivalent to the posterior mode for decent sample size for this calculation. So what's the first term? It says, take the logarithm of the likelihood function and evaluate it at the MLE. But because the MLE is the thing that maximizes the logarithm of the likelihood, that first term is just the maximum log likelihood value of the model that you're working with. So the first term is the maximum log likelihood value. The second term, unfortunately, is what? The logarithm of the what distribution? Forget about the hat on top of the gamma j. What distribution is that for gamma j? Is it the prior or the posterior or something else? It's the prior. So unfortunately, there's still a term that involves the prior. We're supposed to take the prior and evaluate it at the MLE and take the logarithm. And that's a number that has to get stuck in here. That term is still going to create the kind of instability that we're worried about, because that could be all over the place depending upon how we define the diffuse prior. Look, then it goes plus kj over 2 log 2 pi, where kj is the dimensionality of the model, how many terms there are in the model, parameters. Then you have to go minus a half logarithm of the determinant of the observed information matrix under that model, which you remember we got by working out the minus the Hessian of the log likelihood evaluated at the MLE. And then the approximation is good up to order 1 over n, which means it's quite a nice, accurate approximation even for moderate sample sizes. So this is a beautiful observation, and Laplace already had it in 1785. And then when he died, everybody forgot it for 125 years, and then it got independently rediscovered by the applied mathematicians under the name saddle point approximations. And after that, someone noticed, oh, that's just Laplace. Probably at that point, some Laplace scholar, when the applied math people started shouting about the saddle point stuff, some Laplace scholar probably wrote a letter to a journal and said, well, you can call it saddle point if you want, but Laplace did it back in 1785. All right, so this is good, except that it still has that log prior term in there. So notice that the prior enters into this approximation through that logarithm of the height of the prior at the MLE. And notice that this is a term that won't go away with more data because it's the prior, right? The prior is just going to sit there. No matter how much more data you have, the prior is just going to sit there. And so in terms that reflect what's going to change as the sample size increases, the entire approximation is order 1 over n, but this thing is order 1, which means it doesn't go away as the sample size increases. So that is a bit of a potential fly in the ointment, which we will solve after our break. So here comes our final break. And so PC Ops, we're going to shut off now for 15 minutes and start again at 4 o'clock. Okay, so maybe Laplace has provided us with a path. If we can somehow figure out how to cope with that log prior term in a way that keeps us from allowing it to become unstable. Well, about 200 years after Laplace, a statistician named Schwartz obtained a different Taylor series approximation based upon a less precise expansion. Laplace was trying to get his expansion accurate to order 1 over n, and Schwartz was just trying to get order 1, order 1. And so he developed equation 19. The term on the left-hand side is identical to what we had before because earlier I was just calling the data set capital D, but in this problem, capital D is just the vector y1 through yn of your observations. The first term on the right-hand side is also identical. It says the maximum log likelihood value, just as before. And what Schwartz showed, or we can now show, that if we take the other three terms that are on the right-hand side of the equal sign and bring them together in a particular way, the result is the following: minus kj over 2 log n plus what's left over is order 1. So that would be a new way to approximate the ingredient that arrives in the numerator and the denominator of the Bayes factor just by exponentiating both sides of that. And look, here's the cool thing. The prior is not there. And so therefore, our attempts to be diffuse in the prior cannot create the kind of instability that makes the Bayes factors go crazy. You would want that number to be big if model J were good. And notice what it does. It's interesting. It makes an explicit trade-off between the log likelihood value attained by the model, which is supposed to be big if the model's any good, because that means that you have found a model that creates large log likelihood values. Therefore, large likelihood values, there you found a model, or you found a model that has a high likelihood. And I'm waving my hands with this. But that number you want to be big. And look at this thing over here. This number, maximum log likelihood, therefore represents the quality of the model fit. And minus kj over 2 log n is an explicit penalty for how complicated the model is. So we want the model to fit well, but we also don't want it to be too accurate. I mean, we don't want it to be too complicated. We would like a model that strikes a nice trade-off between quality of fit on the one hand and accuracy, and complexity on the other hand. And these two terms exactly do that. For reasons connected with an idea that comes up in generalized linear models called the deviance, people prefer to think about maximum log likelihood values on a scale that you get by multiplying them by minus 2. Because it turns out that minus twice the maximum log likelihood value turns out to have a large sample chi-square sort of interpretation. And so people like to take Schwartz's so-called Bayesian information criterion, or they like to take his Taylor expansion and multiply both sides of it by minus 2 and call the resulting thing on the right-hand side with the plus O of 1 term disappeared. We then call it the Bayesian information criterion, BIC value for model J, given the data set D and the background information B. It's minus twice the maximum log likelihood value from that model plus kj log n. And if a minute ago we wanted equation 19 to be big as a support for model J, we now want the BIC value to be small because we multiplied it by a minus sign, minus 2. And so this model comparison method makes an explicit trade-off, and this is the thing that was used in the Bayesian model averaging software that we looked at earlier today, BICreg, the one that came from Adrian Raftery and his people. And this method makes an explicit trade-off between model complexity, which goes up with kj, and interestingly, it goes up with kj at a log n rate. And so you are penalized for complexity more with large data sets than you are with small ones. So it makes an explicit trade-off between model complexity on the one hand and model lack of fit through the minus 2 log maximum log likelihood term. BIC is called an information criterion because it resembles AIC, and I've told you about that before and how Mr. Akike cleverly manipulated the world to name it after himself. He used information theoretic reasoning to arrive at a competitor criterion, AIC, for model J, given the data set and the background information. And look, the first term on the right-hand side is identical. It's minus twice the maximum log likelihood value. And the second term does have a penalty for complexity, but look, Akike's penalty is not driven by the sample size. He just says your penalty is plus 2 kj, whereas the BIC penalty is kj log n. And so n doesn't have to be very large before log n starts getting bigger than 2. And the BIC penalty for complicated models becomes bigger and bigger. So this is why the BIC criterion tends to prefer smaller, more parsimonious models, because the kj log n term is quite a heavy penalty against complex models, especially when the sample size is large. Akaike's approach was trying to optimize along a different dimension, and this is precisely the moment where we see that distinction I was talking about earlier. Akaike was trying to find the model that predicted best out of sample. And for that purpose, the penalty term came out 2kj. Schwartz was trying to find a model comparison method that led to that kind of consistency I told you about before, where you pretend you're in a world where there is a data generating model and that you have it somewhere inside the set of models you're choosing among. And then as more and more data accumulates, you hope that the posterior model probabilities move in a direction where the posterior model probability for the right model goes to 1 and the posterior model probability for all the other guys goes to 0. That turns out to be attainable with a penalty criterion of the form kj log n. So BIC is going to favor smaller models to try to achieve that thing called consistency. AIC is going to try to, it'll end up with somewhat bigger models, and in so doing, it's trying to come up with models that predict well. And they tend to compete with each other. They are two different criteria. Both of them are good. You can't have them both at once. And this provides a kind of Rubicon. Are you going to use a model comparison method that tries to achieve that consistency idea? And I will criticize that idea either this final hour today or the beginning next time. Sounds like a nice thing to want, but actually it isn't necessarily the be-all, end-all. Are you trying to achieve consistency on the one hand, or are you trying to build models that predict a lot of? The second of those two things is very much the standard thing to try to optimize over if you're a machine learning sort of person, right? And so you could say AIC is more for machine learning, and BIC is more for people who think consistency is worth trying to achieve. Soon, we're going to have two other ways of comparing models. One called DIC, which comes from the Winbugs people, and is going to turn out to be a generalization of AIC. And this thing called log scores, which turns out to be a generalization of DIC. So basically what we're going to have is the following Rubicon, which I hinted at before, and I should try to get into the notes now. AIC, DIC, log scores over here. And they're on the side of things called trying for good out-of-sample predictions. And they end up choosing somewhat larger, by which I mean more complex, larger models. Over here on this side, we have Bayes factors and BIC, which is a kind of special case of them. And what they're trying for is this thing called consistency. And this is going to lead to somewhat smaller models, less complex. Consistency means that your ensemble of models you're choosing among, which no longer has to be finite, but could be countably infinite, includes the data generating model in there somewhere. So assumption one, if MDG is in there, then what you would want is for the posterior model probability on MDG, given the data, which is the data set depends on sample size and B, according to this line of reasoning anyway, you would want that to go to 1 as n goes to infinity, and that's what consistency means. So you would want your model comparison method to more and more strongly favor the truth if the truth could be found inside your set. And that does sound reasonable, but it is subject to criticism. And I'll get to that in a little while. So returning now to the main line. Look how Schwartz came up with this equation 19. And it looks like a kind of cut-down version of equation 18 that Laplace had come up with before. So let's try the following exercise. Let's try to pretend that Schwartz arrived at equation 19 with a particular prior distribution that caused the simplification that leads from equation 18 to equation 19. Let's equate all the stuff that's not the same in the two equations to, let's make that come from the prior and ask, in a kind of reverse engineering move, let's ask, what is the prior that Schwartz secretly had in mind so that his approach is a valid Laplace approximation? And it turns out you can figure that out, and it's not that hard. The implied prior that BIC is using from the point of view of the Laplace approximation looks like equation 22. And what it says is that gamma j, which is a vector of length kj, you're assuming a multivariate normal prior for it, and that would make sense if all the elements of gamma j lived on the whole real line and wouldn't necessarily be so sensible otherwise. You're assuming that gamma j as a prior is multivariate normal, centered at the maximum likelihood estimate, and with a covariance matrix given by n times the inverse of the observed information matrix. And it's not that easy to see what that implies, but I will tell you what it implies. This prior is called a unit information prior, where the word unit corresponds to the idea of the number 1. Because in large samples, this prior corresponds to the prior being equivalent to one new observation that matches up with the data in the sense that it has the same sufficient statistics as the observed data. And so the implied prior hidden inside Schwartz's approach is actually from the point of view of trying to create a sense of diffuseness in the prior on the parameters of the model is actually a very sensible thing hidden inside BIC. You would want the information content of your prior to be a small number, and in fact it is. The prior gets 1 vote in a unit information prior setting, where the data gets little n votes, the prior gets 1 vote. And so that means that the prior is diffuse, and yet at the same time, it's constructively diffuse because it's centered in its diffuseness at the story that the data is trying to tell. Now, it may bother you that we have just used the data to specify the prior along with the data specifying the likelihood. And that should bother you initially because of the thing we've been harping on this whole course, that you want ideally for the prior to be a separate external information source. But you can see that that effect must be negligible with even moderate n, because if n is already something like 100, the information content of the prior is a whisper, and the data set is a shout. You got 100 votes from the data and 1 vote from the prior. It's not going to matter much. So my advice to you, as a general matter, and I take this advice myself, except for that paper I wrote with my Greek colleagues, is that if you're going to go in this column over here, forget about Bayes factors in general, which have the possibility of leading you badly astray if you put in the diffuse priors in the wrong way, and go with BIC, which is a special case of Bayes factors, BF for short, special case of BF with a unit information prior. And that's a very sensible thing. So that's why I'm happy to use Adrian Raftery's software for doing model averaging and regression models and logistic regression models and so on, because he's using a variant on Bayes factors in which we are protected from our worst impulses. That thing I said before about stop me before I harm myself again, stop me before I kill again. BIC is a way to stop myself before I harm myself again. I don't have an opportunity to put a prior into BIC because it's already in there. It's the unit information prior. Centered at the same story the data is telling. And so all of the nasty excesses that can arise from injudicious use of Bayes factors by bringing in prior information that could blow things up and so on, all of that disappears. So like it says on the top of page 56, the BIC approximation to Bayes factors, I need to go back, please. Yes. Has the extremely desirable property that it's free of the hideous instability of integrated likelihoods with respect to tiny details in how diffuse priors are specified that do not arise directly from the science of the problem. In my view, if you're going to use Bayes factors to choose among models, you're well advised to use BIC or some other method that protects you from yourself in misspecifying those tiny details. Yes, please. Yes. It is always okay to ignore that order 1 term, because in the actual BIC expression, it's not there. Basically, what we're doing when we're comparing two models is we're hoping that the order 1 terms approximately cancel. Because we're going to go BIC of one model minus BIC of the other one, and we're hoping the order 1 terms cancel. And that turns out to be reasonable. So basically, we make equation 19 operational by ignoring the order 1 term. Now that we've seen BIC, and I've argued that it's a good thing to do, when can it not be used? Well, it only has 2 terms in it. What about the first term? When you have any parametric model you're working with, can you always work out the maximum log likelihood value? Answer, yes. The log likelihood is just a function. You can always find the MLE and evaluate the log likelihood function at the MLE and hit it by -2. So there's nothing wrong with the left-hand term. Nothing can ever go wrong with that in a parametric model family. But what about the KJ log n term? To make that operational, obviously you need to be able to count n, and in a data vector that's just y1 through yn, that's not a problem. But you also need to be able to count KJ. And so actually both of those issues are a bit of a challenge when the data set has a hierarchical modeling character. So yes, thank you. True. When BIC can't be used. When n and or KJ are hard to count. Example, aspirin meta-analysis. Remember the model? Yi given theta I, we're independently normal theta I with known variance VI. Pretend those are known. And I indexes study that we're combining in a meta-analytic sense. And then the theta i's given mu and sigma squared were regarded as IID normal mu sigma squared, and then we had a prior on mu sigma squared, for example, diffuse. I runs from 1 to k. We had k studies in our earlier work, and j runs from 1 to n sub I. Let's call this number capital I instead to keep from confusing things. So in our earlier aspirin study, we had 6 studies, and the n sub I, actually there is no j in this story. There is no j, because we're not indexing things down to the patient level. But each of the yi's is based on nj patients, n sub I patients rather, and these numbers were on the order of 1,000 to 5,000 in each study. So I would like to use BIC to compare one hierarchical model, this is one of them, with another one. For example, I could try putting T, random effects, into the model and try to calculate BIC to compare them. But what's the N and what's the KJ that go into KJ log N? There is no obvious and unique definition for the number of parameters in the model. Because in fact, it turns out that there's a notion of number of effective parameters in the model that has to do with how much information is really coming in a within and between study sense. I told you for some purposes this model behaves more like the effective sample size is 6, and for some other purposes it behaves more like the effective sample size is 5 or 10,000 for the patients. And so BIC basically throws up its hands right here and says, it can't be done. I can't use it because I can't find the KJ, I can't find the N. AIC has the same problem because they're both driven by KJ. And in fact, one of the reasons that Spiegelhalter, the guy who helped to develop the WinBugs code, one of the reasons they developed DIC is precisely for this purpose, to try to create a version of AIC that would work both for ordinary models where you can count how many parameters there are and also for hierarchical models where you can't. And pretty soon we're going to get to DIC, I think. So that's just a little interlude on the topic of when we can't use BIC. The other method I like better, log scores, can always be used, and I should tell you more about them now. Log scores are based on my third principle of the 4 principles that I want to share with you in this unit of the material, and it might as well be called the prediction principle. And it simply states something that I hope we all would agree is true, that good models make good predictions and bad models make bad predictions. In fact, that particular bright red line between them is one scientifically important way to know a model's good or bad. So if you start from that prediction principle right away, it suggests that you ought to try to build a generic utility structure based on predictive accuracy. So let's consider first a setting in which the data set is just that vector of real numbers, y1 through yn. And the models to be compared are, as before, parametric models where each model has its own parameter vector gamma j. Well, once again, we face that issue that I mentioned several times ago. When you use posterior predictive distributions to see how good a model is, and that's what the prediction principle says to do, evaluate the quality of predictions, you are automatically in the business of doing something that looks a little uncomfortable. Namely, here's my predictive distribution for observation 6, given, let's say, the entire data vector y and b in a setting where n is large, and so it doesn't matter very much whether we use observation 6 over again on both sides of the conditioning bar. And this is where y6 actually fell. Whereas over here in this other predictive distribution, for Y19, this is where Y19 fell. So we can all look at those two pictures and say, somehow the prediction process did a better job with observation 6 than it did with observation 19. But now we actually have to commit to something in which we come up with an explicit measure of the distance between a single point on the one hand and an entire density function that's used to try to predict that point. And as I mentioned before, there are a number of possible ad hoc ideas. You could draw a standard unit scale and find the posterior predictive mean and the posterior predictive standard deviation. We could call this number mu hat and this number sigma hat. And you could calculate a z-score for observation 6, which is y6 minus mu hat over sigma hat. And informally, you could say that this one did pretty well if the z-score is somewhere between -2 and +2, the sort of thing we often do with normal curves, right? You could do that. But that's kind of ad hoc, it turns out. If you did that, of course, Y19 wouldn't look so good by the same standard. But people have developed a theory about this. The theory says what you ought to do is see how tall the predictive distribution is right at the point that actually occurs. That would be the height of the predictive distribution at that point. And now take the logarithm of this height. So each observation in the data set is going to give you the logarithm of the height of its predictive distribution, the height that actually obtains. And you get one number like that from each observation. And since the observations are exchangeable, it's natural to combine them just by adding up across all of them, giving them equal weight. And while you're adding, you might as well average. And so I'm going to call that thing the full sample log score. And this should have been conditional on model J as well. For model J, given the data vector Y and the background information B. So LS stands for log score. So like it says at the top of page 57, when comparing a future data value Y star with the predictive distribution for it under model J, it's been shown that under reasonable optimality criteria, all optimal scores measuring the discrepancy between Y star and that predictive distribution are linear functions of the logarithm of the height of that density function at the point Y star. So using this fact, perhaps the most natural looking form of a kind of composite measure of predictive accuracy for model J is what you might as well call a cross-validated version of the resulting log score, LSCV for short, CV for cross-validation. And it's the same idea, except you only condition on the data vector with observation I omitted to create the predictive distribution. And then you predict the observation that got set aside. And my student Milovan and I, a few years ago, explored the capability of cross-validation log scores to accurately discriminate between different classes of models. And while we were at it, we thought we would go ahead and try the full sample version because it was going to be computationally faster. Because after all, a naive implementation of equation 24 would require you to compute little n separate predictive distributions, because every time you take an observation out, you get a slightly different predictive distribution. And it's hard to say how you ought to change each predictive distribution a little bit to accommodate a new observation coming in and another one going out. It's hard to do that. So we invented this full sample log score idea over here as a way of creating a computational shortcut, because you only have to create one predictive distribution for the whole process of evaluating the log score. And we were fully prepared to discover that we would have some advantages and some disadvantages by this idea of full sample. The advantage would be computationally faster. The disadvantage would be maybe it didn't do as good a job in comparing models. And remarkably, we found that the full sample log score actually can have better small sample model discrimination ability than the cross-validation approach, in addition to being faster to approximate in a stable way. So it's a little bit like Christmas having come early. You thought that you were going to have to gain something and give something up, and in fact, you gained and gained both. Now, having bought the calibration principle, that makes it appropriate to think about the existence of an underlying data generating model, MDG. And as was pointed out to me by a guy in machine learning named David Bly, full sample log scores have a nice interpretation as an approximation to what people call the Kullback-Leibler divergence between the data generating model and the predictive distribution for future data. The Kullback-Leibler divergence is the way it's written is the expression on the left-hand side of equation 26. You read that out loud, the Kullback-Leibler divergence between the model MDG and the predictive distribution P of dot given Y and MJ and B. That turns out to be defined to be the following thing. It's the difference of two expectations. It's the expectation of the logarithm of the data generating mechanism with respect to the data generating mechanism minus the expectation of the other distribution with respect to the data generating mechanism. And so you can see that that has an asymmetry to it. If I reversed the roles of MDG and the predictive distribution, I would get a different expression on the right-hand side. And the asymmetry is in there on purpose because you're supposed to use this as a measure of how far apart two distributions are when one of them is regarded as the right answer and the other one is regarded as the approximation to it. And the one that's regarded as the right answer is the one that's to the left of the two parallel vertical lines. But look, we can now simplify the right-hand side. The first term on the right-hand side of 26 does not change as you go from one data set to another or even as you go from one model to another. So it's just in there as a kind of constant from the Kullback-Leibler point of view. But look, the log score, look at the expression 25. It says, let's average over the logarithm of the predictive distribution, where the averaging is with respect to the right data generating model. And in fact, the right data generating model is nicely approximated by the empirical CDF, which puts mass 1 over n on every single point. And so the right-hand side of equation 25 is in fact an approximation to the far right term in the left equation, or I'm sorry, in the top equation in expression 26. And so minimizing the Kullback-Leibler divergence between the right answer and your particular predictive distribution arising from model J is exactly equivalent to maximizing full sample log score. So that's a nice argument that demonstrates that another way to see why full sample log scores are good. They correspond to trying to minimize the distance between, it's not quite a distance measure, but it's like a distance measure, the distance between what you're using as your best understanding of a predictive distribution for future data, namely the thing that comes from model J, and the actual true data generating mechanism. How do you calculate log scores? Well, I showed you, except that I didn't get the numerics to work out right, and I'll fix that for next time. It turned out that several of the files were corrupted, and they produced numerical results, but wrong numerical results, and I'll fix that for next time. But now we come to a point in the story where I've offered you two quite different Bayesian methods of comparing models. Log scores on the one hand, BIC on the other hand. assuming that BIC is implementable. And the principal guidance I've given you to choose between them so far is this little chart on page 3 of the handwritten notes today, where we see that, as a general matter, you should favor log scores if you're trying to go for good predictive accuracy, whereas you should choose potentially Bayes factors, namely BIC, when you're trying for this thing called consistency. Well, let me make a couple points that are at least mildly critical of this consistency point of view. It sure sounds like something that you would want. Wouldn't you agree? If you pretend that the truth is hidden somewhere in the ensemble of models that you're comparing, wouldn't you want it to be true that as that ensemble remained completely fixed, but you got more and more data, your posterior model probabilities would concentrate more and more on the right answer? Doesn't that seem like a good thing that you'd want? But what about the following? Is that particular way of imagining getting more and more data an accurate reflection of what would really happen if you were trying to build models from the data that approximate reality? Think about your own modeling work. You start with a simple model with a small data set because you know that the model simply cannot be too complicated because you don't have much data. In particular, as we've seen, n conditionally IID data points cannot support a model with more than n parameters in it. But now the data starts to accumulate. The floodgates open. You set up one of these Silicon Valley data gathering exercises where you run a randomized controlled trial and you let it run for 2 weeks. And you end up with 12 million observations in the treatment group and 12 million observations in the control group. Are you still scientifically content to fit that same simple model that you would have been prepared to fit with only 50 observations, the one where you have 24 million observations? No. Your scientific impulse is going to be to allow the complexity of your models to grow with sample size. And you want to do that to do a better and better job of reflecting reality. You really would have wanted to have lots of parameters in that data set with n equals 50, but you know you can't because you've only got 50 observations. So the asymptotics that are at the heart of consistency are the wrong asymptotics. Because what are they? They are the asymptotics in which we don't let the models become more complex. We keep them all the same. In other words, the ensemble that's supposed to have the truth in it is not allowed to change in the consistency asymptotics. It stays the same. And we simply let n get bigger and bigger and see what happens. But that's not a realistic asymptotics, because the realistic asymptotics comes from letting the complexity of the models in this ensemble grow as well as sample size growing. And no one knows how to prove any asymptotics in that setting where you let the ensemble grow in a way that is a realistic reflection of how people actually build models. There are no asymptotic results I know of for that. Here's another even simpler argument why I don't personally care that much about consistency. Jim Berger, one of the most prominent Bayesians still working today, gave a workshop at Santa Cruz last summer, and he basically said categorically that he would never use any procedure that wasn't consistent. In fact, I think there's a politics to his statement that runs something like this. And Jim, if you ever watch this video, I'd love to talk about this with you over a good martini, because he and I are both gin drinkers when we can find good gin to drink. He said, I would never use a method that's not consistent. In other words, that doesn't have the right behavior at infinity. But I will now take that argument and, I believe, demolish it as follows. By that argument, you should never be prepared to take 2 aspirin when you have a headache because it would be bad for you to take infinitely many aspirins. You get a bad result with number of aspirins equals infinity. So therefore, you shouldn't take any aspirins at all. The method called taking aspirin to make your headache go away is not an asymptotically consistent method because more and more aspirins does not lead to more and more pain relief. Instead, it does. It leads to permanent pain relief. That's true. For a while, it leads to temporary pain relief as you go from half an aspirin to 1 to 1.5 to 2, perhaps. But then at a certain point, it leads to permanent pain relief. That's right. And so isn't that an argument that basically completely demolishes the consistency idea? In other words, and here's the point I'm making. I don't care what happens if I have 100 billion observations, because I don't have 100 billion observations. I want to know the actual real-world operating characteristics of various ways of learning about the world with my sample size, not with some sample size that's artificial or that can be manipulated to be arbitrarily large because the arithmetic, the math, turns out to be easy to do. In other words, what I want is a kind of analysis that says, all right, I know I'm going to have, let's say, 842 observations, because that's the nature of my data gathering. Let's now do some studies in which we compare various ways of trying to find out truth with data sets that are like the data set I'm going to get with 842 observations in them. That's my version of, it's a kind of my sample consistency rather than n equals infinity consistency. And I think that's where we all should be, right? Because we do know we've got this much data. The data set's right in front of us. It might get bigger if we run the experiment longer, but we're trying to figure out what's going on right now. So there's the data set. We know what the little n is. With a data set of that size that has behavior similar to what I'm seeing here, if I have two different ways to decide which model is better than which other model, let's go ahead and make studies in which we compare those two methods there for my sample size. Now that's a little bit of work, but it's not work that's too hard because we are all in the whole room in the process of where all of us are computer fluent. We're all good at simulating. That's what we do all day long in one way or another. We answer most questions these days, not with analytics because the problems are too hard. We answer most of them with simulation these days. So I can perfectly well create a simulation environment in which all the simulated data sets have the same sample size as mine and are variations on the basic theme that I see in my data set. For instance, I could bootstrap my data set and get other data sets that are interesting and useful perturbations of this one, reflective of what I might have gotten if I ran the experiment next week instead of this week. I can bootstrap my data set, take a sample of size 842 in an IID, in other words, at random with replacement manner, and do that over and over again, not for the purpose of drawing inferential conclusions, but for the purpose of simulating data sets that are like what I would get if I ran the experiment next week instead of now. And run my different methods for seeing what's going on all those bootstrap data sets and keep score, because I can create a world where I know what the right answer is. My data set with n equals 842 is the truth in that world where I'm bootstrapping from it, so I know what the truth is. And I can now see which of these two different methods is better at recovering the truth. So from that point of view, I would like to share with you a comparison between log scores on the one hand versus BIC on the other hand. So here's going to be something like a prize fight where we pit them off against each other in a battle in a world where we know what the right answer is, and we look and see what happens. So what follows is a sketch of recent results based on simulation experiments with realistic sample sizes. And here I'm trying to say some of the objections to the usual the usual consistency story. In my view, standard asymptotic calculations, choosing between model 1 and model 2 as n goes to infinity with the ensemble script m just consisting of model 1 and model 2 not changing, remaining fixed, Asymptotics like that are essentially irrelevant in calibration studies, and here are two reasons why. First reason I mentioned already, with increasing n, you'll want script m to grow to satisfy your desire to do a better job of capturing real-world complexity. And reason two, which I haven't mentioned yet, but which is also worth paying attention to, particularly if you are involved in anything that has to do with economic data. Data usually accumulate over time, and with increasing n, it becomes more likely that the real-world process you're modeling is not stationary. In fact, that should be a concern of everybody here in the Valley who's doing these A/B testing experiments, because the longer you run them, the more likely it is that the world outside your company is changing, and that the thing you're trying to study is not stationary, so that the results in week 3 might not be comparable to the results in week 1, because the world around you is changing. And so asymptotics that pretend that n gets arbitrarily large with the snap of your fingers, rather than having to wait over time to get more data, are irrelevant to real practice a lot of the time as well, because they assume a kind of stationarity of what you're studying that is not likely to be absolutely true in what you're working with. Now, people have invented various versions of Bayes factors that have propped up this problem I've shown you today, and that do behave sensibly with diffuse priors on the model parameters. Cousins of intrinsic Bayes factors, more recent cousins like expected posterior priors, and Berger and Paricci have been at the forefront of this work, and it's great that they've been doing it. These versions tend to have model discrimination performance that are similar to that of BIC in calibration environments where I do repeated sampling with known data generating mechanisms. So I'm going to show results for BIC here as compared with log scores. So consider assessing the performance of a drug for lowering systolic blood pressure in hypertensive patients in a phase 2 clinical trial, and suppose that possibly after suitable transformation, a Gaussian sampling distribution for the outcome variable is reasonable. Then we often see in biostatistical work two basic designs that come up quite often. One of them I'm going to call quantifying improvement, and the other one I'm going to call establishing bioequivalence. So in the quantifying improvement design, what I want to do here is to estimate the mean decline in blood pressure under this drug. I'm not going to compare it with another drug, but I'm going to see how well it lowers blood pressure for these people. So a pretty natural design would be to run the repeated measures or pre-post experiment, where we measure the systolic blood pressure of these people before they started taking the drug and the same people after they took the drug for a suitably long period of time, so that the drug's effect could become apparent. So the data consists of Y sub I for patient I is the observed difference, systolic blood pressure, SBP for short, systolic blood pressure before minus after for that patient. That's just a number that we hope is going to be positive if the drug is working. And now think about those numbers not in your sample, but back in the population of people that you're trying to generalize to. Everybody with hypertension, for example, if your patients in your study are like a representative sample from that particular population, then imagine running the experiment on all of the people in the population, not just the ones in your sample, and let theta stand for the mean difference across all those people. So theta is the unknown here, and we are trying to do inference about it, pretending that the yi values are like IID draws from a normal distribution with mean theta and some variance, sigma squared. Now, the real-world purpose of this experiment is to decide whether to take the drug forward to the next phase in clinical trials. I'll just tell you that's what we're trying to do here. But the 20th century, if you look back on it, it looks like an almost exclusively and relentlessly inferential century. This is a problem about decision making, and yet all the tools that were invented in the 20th century, almost all of them, especially all of them from a frequentist point of view, are inferential in character. Did I tell you the history behind that? Did I tell you about that man Abraham Wald? Okay. The Bayesian decision theory story came from that guy, Frank Ramsey, who was an undergraduate at Cambridge and published a paper in a collection of papers by various people in a book in 1926, in which he showed that the right thing to do was to lay out those ingredients we've talked about and maximize expected utility, where the expectation is over your posterior distribution that brings together your prior information and your data information. So other people became aware of this work. Unfortunately, Ramsey, shortly after that, died of a disease that was at the time incurable. I think it had something to do with his liver. And even though he was dead and was not out there popularizing his results, a lot of other people were, because they were very impressed with him when he was alive. I think I may have mentioned before that if he had remained alive, he would no doubt have been one of the most influential Bayesian statisticians in the whole world in the 20th century. But we lost him at an age of something like 28 or 29 years old. But he had made a big impression on John Maynard Keynes and other prominent people, and so they started talking about his results, and so they got widely known. And in the late 1940s, a prominent frequentist named Abraham Wald said to himself, well, Ramsey already showed what to do from a Bayesian point of view, but I am a frequentist. I, Abraham Wald, am a frequentist. I'm going to write a book in which I show that we frequentists can do just as well as the Bayesians do with Ramsey's approach. And to Abraham Wald's surprise, what he ended up proving instead was quite the opposite, namely that he proved a theorem that can informally be stated as follows: all good decisions are Bayes decisions. In other words, in any particular decision problem, all of the decisions that appear good from a frequentist point of view could equally well have been derived by writing down a Bayesian model with some particular prior distribution and following through with Frank Ramsey's prescription. And moreover, the Bayes decisions were where all the good decisions could be found. You can't find any bad ones in there. They correspond to some sort of prior set of information, whereas the frequentist approach suggests a whole bunch of decision rules, all of which are really, really bad. And so the frequentist story gives you an immense number of rules. Most of them are really bad, and all the good ones are Bayes rules. And if Wald had been doctrinaire about the frequency story, he might just have burned that material. But instead, he was an upright scientist, and he published it. And you can read the book. It's still in print. And basically, it's one of these to my surprise sort of books. And as soon as frequentists read this, the process of using decision theory in practical real-world settings from a frequentist point of view immediately stopped, because the frequentists had worked out that they had no competitive advantage. And they focused on the thing that they thought they did have a competitive advantage on, which was inference. And they spent the latter half of the 20th century, Wald did this in 1950, and then he had something tragic happen to him also. 6 months or so after he published that book, he was flying to India to give a talk about it, and the plane crashed, and he and his wife and everybody else on the plane died. So, what's that? Yeah, conspiracy, clearly, that's right. Anybody interested in decision dies mysteriously. Yeah, let's hope not. So there was a lot of mathematical statistics done from about 1950 through about 1975 or 80 from the frequentist point of view, using Bayesian decision theory to create good frequentist estimation methods. And that's certainly one way in which the frequentists used the Bayesian story. But to actually solve real-world problems, like deciding whether to take a drug forward to the next phase of a clinical trial, frequentist methods were never specifically developed for that. So imagine you're a practicing statistician in the latter half of the 20th century, and you don't know the Bayesian story, and even if you did, you can't compute the integrals. And yet you have a decision to make, and all you have is frequentist inferential tools. Then you know that saying about if all you have is a hammer, everything looks like a nail to you. What people started doing was taking inferential tools like Neyman-Pearson hypothesis testing and use them as hammers on decision problems, even though they were strictly speaking only meant for inferential problems. And what you can do to undo that damage is to reverse engineer people's incorrect use of something like hypothesis testing in a decision problem and work out what the implied utility structure is for that method and discover that it's a bad utility function. So I'm going to show you that. I won't be able to show it all of it today because we're almost out of time, but like it says at the bottom of page 60, under the weight of 20th century inertia, in which decision-making was strongly and incorrectly subordinated to inference, your first impulse might be to treat this as an inferential problem about theta, but it's not. It's a decision problem that involves theta. And this brings me to my fourth and final principle in this set of material, trying to help us with Bayesian model specification. Namely, we should all get out of the habit of using inferential methods to make decisions because their implicit utility structure is often far from optimal. If you recognize you have a decision problem, then set it up as a decision problem and maximize expected utility. The action space here only has two actions in it. Script A has just A1 and A2 in it. Either don't take the drug forward to phase 3 or do take it forward. There isn't any way to take it partway forward. It either goes forward to phase 3 or it doesn't. Now, a sensible utility function, which would depend both on AJ and theta, should actually be continuous and monotonically increasing in theta over a broad range of positive theta values. In other words, a drug that helps people with hypertension lower their blood pressure by 40 millimeters of mercury is better than one that helps you lower your blood pressure by only 11 millimeters of mercury when you're a highly hypertensive person. And it's better, it might even be 4 times better because it gets you 40 points down rather than only 10 points down, for example. So the utility function should actually depend upon how big theta is and be monotonically increasing in that, possibly even linearly over a particular range. Of course, if you invented a drug that took people's systolic blood pressure from 190 all the way down to 45, that wouldn't be so good either because the person would be fainting at that point and might even die under the influence of that drug. So it can't be monotonically increasing over the entire range of possible theta values representing a drop in blood pressure because pretty soon you're going to start fainting or dying. But anyway, it should go up for a long time and then go back down again in a region where you wouldn't want it to be anyway. But to facilitate a comparison between BIC and log scores and also between this approach and hypothesis testing, I'm going to compare two models, M1 and M2, that do the standard frequentist impulse, namely dichotomize the theta range. Either theta is bigger than or equal to something or else it's less than something. And here's another inertia thing that happens, and after this we'll wrap up for this week. Here's another inertia thing that happens. If you look back in your textbooks, your Statistics 1 textbooks, they're all the time having you test the hypothesis that theta is exactly equal to 0. But in a problem like this, there's nothing special about 0. 0 represents the drug having an average improvement, an average decline in blood pressure of 0 millimeters of mercury, and that certainly would not be a good drug to take forward. But what if I had a drug that lowered people's blood pressure on average by 3 millimeters of mercury? Then it does have a modest health benefit, but it's too small to be worth taking forward to phase 3. So 0 has no special meaning in this problem. Instead, the choice should be based upon whether theta is greater than some number delta or less than or equal to delta, where delta is a positive number representing a kind of practical significance threshold. And it's probably some number on the order of 15 millimeters of mercury or so. If you developed a new blood pressure lowering drug and it didn't lower people's blood pressure by at least 15 millimeters of mercury on the systolic scale, then probably there's no point in going forward because we already have Lipitor and all these other drugs that are good. I guess Lipitor is for cholesterol. I've got the wrong drug in mind. But we have a bunch of good blood pressure lowering drugs already that have a typical effect that's quite a bit bigger than 15. And so, in fact, the right thing is to wonder whether theta is greater than delta or less than or equal to delta. And so equations 27 and 28 make that operational. Both of them assume that the data are Gaussian with mean theta and some variance sigma squared. But under model 1, the prior is diffuse for theta values less than or equal to delta. That's like saying under the hypothesis that theta is less than or equal to delta. And model 2 has the same sampling distribution, but works with a prior that's diffuse for theta values that are bigger than delta. that in this way, we can rephrase what would have looked like a hypothesis testing problem and make it into a model comparison problem, because you have the same exact sampling distribution, but you have a different prior in each case. And that gives rise to different posterior distributions. And we'll continue this next time and, in fact, wrap up the whole course. We're going to meet again here, exactly in this room, 1 week from today. And if you have particular ideas that you would like me to try to cover, at least briefly, in the sense of mentioning them and bringing references, for instance, that you could begin looking at, please email me with these ideas between now and, let's say, next Wednesday or so. And I will attempt to fold them into the material I'll prepare for next Friday. So thanks once again for your patience in going through all these many hours of this, and I'll see you next week. So VC Ops, we're shutting down for the day. Thanks.